deep breath, settle into comfort, and let your body unwind as you listen. This calming video blends soothing narration with fascinating science, designed to ease stress, quiet your thoughts, and guide you toward rest. Relax, let curiosity drift gently, and enjoy a peaceful journey that helps you sleep deeply while learning something new. Light has always been there, written into the fabric of human experience like a silent companion. Before words were carved into clay, before history was bound in scrolls, before cities shimmered with glass and stone, there was the glow of fire against the night. Imagine the first humans huddled in a cave, shadows swaying as flames danced, every flicker of light holding back the dark that pressed at the edges of vision. That glow was more than warmth. It was survival, guidance, and mystery. Even now, thousands of years later, with our satellites and supercomputers, light still escapes a complete explanation. We have split it into colors, turned it into numbers, and bent it through equations. But when you ask the simplest question, what is light really? The answer remains strangely unfinished. The candle flame and the starlight are the same phenomenon, separated only by distance and scale. A candle flickers because air feeds its fire unevenly, while a star burns in a storm of nuclear fusion, its light traveling across empty space for millions of years before striking the back of your eye. And yet both feel familiar. That duality of intimacy and infinity is why light has always carried a sense of awe. Ancient peoples treated light as sacred. Egyptians worshipped Ra, the sun god. Greeks told of Helios driving his chariot across the sky. In countless traditions, light meant knowledge, hope, or divinity. Darkness was ignorance, evil, the unknown. Light was truth, safety, the known. But as comforting as those stories were, they never explained what light actually was. When you stand beneath the night sky and stare upward, you see dots of light that began their journey long before you were born. Every star above is a memory in transit, the record of an event far away. The pale orange glow of Betelgeuse, the faint white shimmer of Vega, the milky swath of our own galaxy, all of it is ancient. Light is a messenger carrying information across impossible gulfs. But even as we depend on it to reveal the universe, we do not truly know what rides upon it. Is it a wave? A particle? Both? Neither? This puzzle has followed science for centuries, reminding us that light is not only an everyday comfort, but also one of the deepest mysteries in physics. Our earliest ancestors may not have asked those questions in the language of physics, but they lived in light's rhythm. Days were carved by the rising and setting sun. Seasons were tracked by the angle of shadows. Navigation across oceans depended on constellations etched into memory. Farmers watched the length of daylight stretch and shrink, timing harvests to light's seasonal cycles. Even sleep and wakefulness are tied to light, our bodies wired to a circadian clock that rises with dawn and dims with dusk. In that sense, light is not only external, it is woven into us. Every cell responds to its pattern. We cannot exist without it, yet we cannot completely define it. Fire was the first tool that made light portable. A flame could be carried into darkness, an ember could be nursed into a blaze. The torch extended human reach, turning night into a time of activity rather than fear. Later, lanterns, lamps, and eventually candles became the technology of light. Each flame was a tiny sun, tamed and carried. To this day, a single candle in a dark room transforms space into sanctuary. The human eye is drawn instinctively to it, not just for what it illuminates, but for what it symbolizes. Candles still burn in temples, at vigils, in moments of grief and celebration. The flame is fragile yet powerful, a reminder of how dependent we are on something as elusive as light. The stars overhead were the second great revelation. Unlike fire, they could not be controlled. They could only be observed. Their regular rising and setting gave humanity its first calendars, its first sense of cosmic order. The ancients noticed patterns, constellations that repeated each year, planets that wandered strangely among the stars. Light from the heavens became the first data, carrying secrets about motion and time. It was through light that astronomers like Galileo later glimpsed the moons of Jupiter and craters on the moon, shifting humanity's place in the universe. Even then, no one could answer why light made such journeys possible, or what exactly it was that traveled through space so faithfully. Modern science has built extraordinary tools: prisms, telescopes, particle detectors. But the paradox remains. A photon, the supposed particle of light, has no mass. Yet it carries momentum strong enough to push a spacecraft with solar sails. Light moves at a constant speed, the fastest anything can travel. But why that speed has the value it does is unanswered. Shine light through a prism, and it breaks into a rainbow of colors, each corresponding to a different wavelength. Yet that rainbow tells you only what light does, not what it is. The double slit experiment shows light behaving as both wave and particle, depending on how you look, but no definition has fully reconciled this duality. Light reveals everything and hides itself. This is why, even now, light feels as mysterious as it does practical. Without it, plants cannot photosynthesize, the earth cannot sustain life, and human society cannot function. Our eyes evolved to see a very narrow band of the electromagnetic spectrum, the rainbow of visible light. But beyond that lie ultraviolet and infrared, microwaves and gamma rays, all forms of light invisible to us. Bees can see ultraviolet patterns on flowers, guiding them to nectar. Snakes detect infrared heat from prey. Our limited perception means that even the light we depend on daily is far bigger than we can experience. The candle's glow is just one slice of a much larger story. When scientists say light is energy traveling through space, they are not wrong. But the moment they try to pin down what that means, contradictions arise. If light is a wave, what is waving? If light is a particle, how does it spread out and interfere with itself like ripples on water? If it is both, how can it switch depending on observation? These are not small details to iron out. They are reminders that we are brushing against the edges of understanding. Light is not just another physical phenomenon. It is a riddle at the foundation of reality. And yet, for all its mystery, light is also one of the most intimate sensations. A sunrise spilling into a room, a candle flame flickering during a power outage, the glow of a phone screen in the dark. These moments remind us that light is a presence, almost alive. Poets call it divine. Artists use it as their paintbrush. Scientists treat it as a probe, shining lasers into atoms or telescopes into galaxies. Philosophers see it as metaphor, the illumination of truth. Light is practical and poetic, measurable and mystical, ordinary and extraordinary. It defines both the cosmos and the human imagination. Consider how central light is to human language. We speak of enlightenment, of seeing the light, of shining a light on hidden truths. Darkness means ignorance, confusion, fear. Light means clarity, understanding, hope. Every culture equates illumination with wisdom. Even in religion, creation often begins with light. Let there be light is not only a scriptural command, but also a timeless metaphor for awareness sparking in the void. This linguistic weight is not accidental. It reflects a deep intuition that light is not just a tool, but a mystery that defines existence itself. From a scientific perspective, light continues to surprise. We can harness it for fiber optics, sending messages across oceans at nearly the speed of light itself. We can bend it with lenses to peer into cells or across the universe. We can trap it in lasers, amplifying its purity until it can cut steel or perform delicate surgery. And still, the simplest question remains unresolved. Light is energy without mass, both wave and particle, constant yet elusive. A candle in the dark and a star in the sky share the same essence, and that essence defies complete explanation. This is the paradox that makes light both practical and dangerous, in the sense that it reshapes how we think about reality. Every time humanity believed it had light pinned down, new discoveries fractured that certainty. First it was a wave, then it was a particle, then it was both. Now it is something stranger, bound into quantum fields we do not fully comprehend. And perhaps this is why light fascinates us so deeply. It is the companion we know best and understand least. It touches every moment of our lives, but it remains beyond our grasp. So when we think of a candle in the dark, we are not only seeing a flame, we are seeing the echo of the sun, the story of atoms releasing photons, the unsolved puzzle of nature itself. That tiny flame holds within it the same questions that trouble physicists and inspire poets. It is warmth, guidance, and mystery. It is the oldest companion of humanity, and yet it is still the greatest unknown. To look at light is to stare at the heart of the universe and realize the heart keeps its secrets. In the middle of the 17th century, when candle flames were still the brightest points of domestic life, and the heavens could only be studied with fragile hand-ground lenses, one curious man bent his gaze towards something deceptively simple, a beam of light slipping through glass. His name was Isaac Newton, and though history remembers him for falling apples, gravity, and the calculus of the universe, one of his most haunting experiments began with a narrow slit and a crystal prism. What emerged from that experiment was not merely color, but the beginning of a centuries-long struggle to understand what light truly is. It was the first step towards shattering the illusion of white light's simplicity, and the first clue that light contained mysteries deeper than philosophy had dared imagine. Picture the scene: a darkened room in Cambridge, a single shaft of sunlight forced through a pinhole, directed carefully through a triangular piece of glass. The beam stretches, bends, and then bursts against the far wall into a band of color, red fading into orange, yellow into green, blue into indigo, violet at the farthest edge, a rainbow carved from the daylight itself, not in the sky after a storm, but summoned inside four walls by human hands. For centuries, people had seen colors split in rainbows and refracted in droplets of water, but few suspected that white light was not pure, not indivisible, but composed of hidden components waiting to be revealed. Newton's prism experiment in the 1660s was an earthquake for how we think about the world. Until then, philosophers and natural scientists often believed color arose from the modification of pure light by objects. White was considered perfect, colors were distortions, impurities. But when Newton split light into a rainbow, then recombined those same colors back into white using a second prism, he demonstrated something radical. Color was not an addition or corruption, but an inherent property of light itself. White was not pure. It was the sum of many. Suddenly, the very notion of light was cracked open, transformed from a single essence into a spectrum of wavelengths, though Newton did not yet have that word. The impact was profound. Imagine living in a time when color was explained as mere accidents of objects. Now here was proof that every candle flame, every sunrise, every star in the sky carried within it a hidden rainbow. The sun above your head was not a sphere of pure golden light, but a fire whose brilliance contained reds, blues, greens, and every shade between, woven invisibly together until glass revealed the truth. The prism became a symbol of discovery, a piece of everyday material that unlocked one of nature's deepest secrets. From Newton's darkened room began the scientific quest to understand light in terms of analysis, decomposition, and recombination. But Newton's prism did more than show a rainbow. It raised unsettling questions. Why does glass bend light differently depending on its color? Why does red refract less sharply than violet? Why does white emerge whole when all the colors are recombined? These questions turned light from something mystical into something measurable. Newton's obsession led him to develop theories that light was made of tiny particles, corpuscles, each carrying a different color depending on its angle of bending. In his view, the spectrum was a map of the behavior of these particles, a framework that seemed solid in an age when mechanics was becoming the language of science. And yet, even here, the mystery deepened. If light was particles, why did it behave like waves in other experiments? Newton's model would later clash with the ideas of Huygens, Young, and Fresnel, who argued that light rippled like water. The prism, however, remained a stubborn witness. Whether particle or wave, light through glass revealed its hidden spectrum, and no theory could ignore the evidence painted across the wall. The rainbow inside the laboratory was undeniable. The cultural resonance of Newton's discovery spread beyond science. Artists began to think differently about color, separating pigments from the physics of light. Musicians and philosophers wondered if colors were like notes, forming harmonies hidden in daylight. Newton himself flirted with this idea, mapping colors to the musical scale, suggesting that the spectrum had a structure like sound. Although the analogy was imperfect, it showed how this new understanding of light spilled into every corner of thought. Light was no longer just illumination, it was a code to be deciphered. Consider how this experiment echoes through time. Every time you see a rainbow, every time a diamond scatters light, every time sunlight catches on the edge of a glass, you are seeing the same phenomenon Newton puzzled over centuries ago. The screen of your phone, the pixels of your television, the lasers guiding surgery, all are built on the principle that light contains colors, and those colors can be manipulated. A simple prism in the 17th century set the foundation for optics, for spectroscopy, for astronomy, even for quantum physics. When modern scientists split starlight with a spectroscope, they read the composition of suns trillions of miles away. They trace the fingerprints of elements, measure the speed of galaxies, even glimpse the chemical hints of planets that might harbor life. All of that rests on the principle first proven when Newton split sunlight in a room with a prism. And yet, even with this triumph, the essence of light slipped further from our grasp. Newton revealed that white light was not pure but composed. He explained how prisms bend light differently by color. But the deeper question remained. What is light? Why does it split into these colors? Why does it bend at all? Why does it move at the speed it does, neither faster nor slower? Newton had illuminated the path forward, but the mystery grew larger with every answer. The candle in the dark had revealed its rainbow, but its essence was still hidden. The story of Newton's prism is also the story of how science advances, one experiment that changes the question rather than closes it. Before the prism, light was an everyday experience, as ordinary as breath. After the prism, light became a doorway into the fundamental structure of reality. Newton himself may not have known where his rainbow would lead, but his curiosity set in motion centuries of discovery and debate, each generation trying to pin down what light really is, and each generation discovering that the answer is stranger than the last. In today's world, we take the prism's lesson for granted. Children in classrooms split beams of sunlight and marvel at the colors. Photographers rely on lenses and filters to capture precise wavelengths. Scientists use diffraction gratings and spectrographs to analyze the faintest glimmers of light from deep space. All of these are descendants of Newton's first experiments. But the awe remains. Stand in front of a prism's rainbow today and you feel the same hush that Newton must have felt. That sense of wonder when the invisible is made visible. Light, at its simplest, is still our guide, still our puzzle. Newton's prism showed us that the beam we thought was pure is layered, complex, filled with secrets. It is a reminder that reality often hides complexity behind appearances, that the everyday can conceal the profound. The candle flame, the morning sun, the starlight above, all are not simple white glows, but the blending of many voices, a chorus of wavelengths singing together until glass teaches us how to listen. And in that chorus lies the mystery. A mystery that begins with a rainbow on a wall and stretches into the very heart of the universe. In the centuries after Newton cast his prism against a beam of sunlight and split white into colours, the question of what light truly is refused to stay silent. The rainbow on the wall proved that light was complex, layered, rich with hidden structure, but the mechanics of its nature remained uncertain. Newton believed in corpuscles, tiny particles streaming through space, bouncing and bending as they met glass or water. It was a vision that fit with his wider universe, a cosmos explained through bodies in motion, gravity binding planets, forces acting on matter. Yet not everyone was satisfied. To others, the dance of light looked less like particles and more like ripples across an invisible sea. This idea, the wave theory of light, did not spring fully formed in one moment, but unfolded through the persistence of minds who dared to argue against Newton's towering authority. Chief among them was Christian Huygens, a Dutch scientist of the late 17th century, who believed that light behaved more like sound than like a stream of bullets. Sound, after all, moved through the air as a vibration, a disturbance passed along from particle to particle, invisible yet powerful enough to carry voices across distances. Why should light not be the same? Huygens proposed that every point a wave of light touches becomes itself a new source of waves, spreading out in all directions like ripples expanding on the surface of water. This was the essence of what would later be called Huygens's principle. With it, he explained how light bent when passing through glass, how it diffracted around obstacles, how it spread beyond a narrow slit instead of casting a sharp line. When Newton's corpuscles struck barriers like pellets and ricocheted according to geometry, Huygens saw soft ripples folding and bending, embracing the edges. The world, to him, was bathed not in streams of particles but in waves pulsing across an invisible medium. At first, Huygens' theory found little ground. Newton's reputation overshadowed him, and for many decades the particle theory remained dominant. But the seeds were planted, and when the 19th century dawned, new experiments breathed life into the wave hypothesis. Enter Thomas Young, an English physician and polymath with a curiosity that wandered across languages, anatomy, and physics. In 1801, he performed what would become one of the most famous demonstrations in the history of science, the double slit experiment. Young allowed a beam of light to pass through two closely spaced slits and onto a screen beyond. If light were purely made of particles, one would expect two bright patches where the particles struck, corresponding to the slits. But instead, Young saw a pattern of alternating bright and dark bands, an interference pattern that could only be explained by waves overlapping, peaks reinforcing peaks, troughs cancelling troughs. The screen became a canvas of evidence that light did not behave like mere particles, but like waves interfering with one another. The elegance of Young's experiment was undeniable. It showed in one stroke that light could combine and cancel itself in ways particles never could. It also showed that the world was stranger than Newton's mechanics allowed. For centuries after, the double slit pattern became a symbol of light's enigma, a phenomenon so simple to set up yet so profound in its implications. To this day, physicists revisit it, finding new layers of mystery as they probe the boundary between waves, particles, and something beyond both. Following Young came Augustin Jean Fresnel, a French engineer and physicist whose contributions refined and expanded the wave theory. Fresnel built mathematical descriptions of how light waves interfered and diffracted, giving the wave model predictive power that rivaled and then surpassed Newton's corpuscles. He showed how polarized light, waves oscillating in particular orientations, could be understood in terms of wave vibrations, not particles. He used mathematics to explain the rings and fringes observed when light passed through apertures or reflected between surfaces. Fresnel's work provided the rigorous foundation that convinced much of the scientific world that light was indeed a wave phenomenon. But waves require a medium. Sound needs air. Water waves need the sea. If light was a wave, through what did it ripple? This question haunted physics for over a century. Scientists proposed the existence of the luminiferous ether, a weightless, invisible substance that filled all of space, carrying light the way air carries sound. Ether was imagined as a universal sea, undetectable except through the waves it transported, stretching everywhere, binding stars and planets in a shared fabric. It was elegant, almost poetic. The universe bathed in a silent ocean whose ripples were light itself. For a time, the ether theory gave comfort. It answered the need for a medium and gave a home to the waves. Yet it also carried difficulties. If ether filled space, did it resist motion? Did Earth drag through it as it orbited the sun? Or did ether flow freely around the planet? Could ether be measured, tested, confirmed? Scientists searched, building elaborate experiments to detect Earth's motion through this cosmic sea. For decades, the ether remained both necessary and elusive, a ghostly presence assumed but never seen. Still, the wave model flourished. Through the 19th century, experiments confirmed the predictions of interference, diffraction, and polarization. Fresnel lenses transformed lighthouses, magnifying beams to guide ships across stormy seas. Interference fringes became tools in laboratories. The mathematics of wave optics explained rainbows, halos, and the colors of thin films like soap bubbles. Even as the ether remained mysterious, the behavior of light as waves seemed undeniable. The universe felt once again comprehensible, patterned in ripples and harmonies, elegant in its consistency. Imagine living in that time. Gas lamps glow in city streets, oil lamps flicker indoors, telescopes stretch their gaze toward distant nebulae, and everywhere the idea spreads. What you see is not particles streaming but waves trembling through space. The flicker of a flame, the twinkle of a star, the gleam of sunlight on glass. Each is a vibration crossing an unseen ocean. To grasp light this way was to feel both comfort and awe. Comfort because the model explained so much. Awe because it hinted at the invisible sea in which all creation swam. Yet, as often in science, every triumph planted the seeds of its undoing. As experiments grew more precise, cracks in the ether theory appeared. Michelson and Morley would one day try to measure Earth's motion through this medium and fail, shaking the foundations of the wave model's assumptions. But in the early decades of the 19th century, before relativity, before photons, the wave theory reigned. It was a vision of elegance, an invisible sea upon which the universe's light rode endlessly. The debate between particles and waves was not just academic. It shaped technology, philosophy, even art. The Romantic poets saw in the wave theory a metaphor for continuity, the boundless interconnectedness of nature. Engineers designed instruments around diffraction and interference. The very vocabulary of science shifted, trading Newton's corpuscles for oscillations, crests, and troughs. Knowledge reshaped imagination, and imagination, in turn, reshaped culture. What makes this period of physics so remarkable is how human it feels. Huygens, gazing at ripples in a pond and daring to say that light worked the same way. Young, standing in front of his screen, watching interference fringes appear like ghostly fingerprints of truth. Fresnel, hunched over equations, extracting precise predictions from abstract waveforms. Each of them worked not with the full picture, but with fragments, glimpses, and each dared to propose that the unseen could be understood by analogy and experiment. Their courage was not in solving the mystery, but in pointing to new paths where answers might lie. The story of light as waves teaches us something deeper about the pursuit of science. It shows that truth is often layered, that models can be useful without being final. Newton's particles explained some things, Huygens' waves explained others. Both carried parts of the truth, neither the whole. Even now, centuries later, physics continues to wrestle with this duality, forced to accept that light may never fit neatly into human categories. It is both wave and particle, and perhaps something beyond our language, rippling on an invisible sea we cannot name. As we look back at this chapter of history, we see more than debates between scientists. We see humanity learning how to see differently. A candle flame was no longer just a flame, but vibrations of light spreading in all directions. A rainbow was no longer mere beauty, but the signature of waves bending through water droplets. Stars were no longer simply points of light, but messengers across the ether. To live in that age was to feel the universe becoming more intricate and yet more accessible, woven of patterns as familiar as ripples on a pond. The candle in the dark had become a wave in the sea, and though that sea remained unseen, it gave a sense of unity, a sense that all of nature's light was connected by rhythms that spanned the cosmos. But the deeper essence of light still lingered out of reach. Every answer whispered of a larger mystery. Every explanation drew closer and then slipped away. The invisible sea comforted and puzzled in equal measure, a stage upon which the drama of science continued. Light has always carried a double life. To the eye it seems smooth, flowing, a wash of radiance that paints the world in color. To the mind, however, it often refuses to behave so simply. Centuries after Newton split a beam of sunlight into a rainbow with a prism, the question of whether light was truly a wave or something else entirely remained unsettled. In the early centuries of science, the pendulum swung back and forth, sometimes toward waves, sometimes toward particles, and each swing brought not only answers but deeper puzzles. What if light was not merely a ripple in an invisible sea, but instead something harder, sharper, more like a shower of tiny bullets or sparks of radiance? For Newton, who shaped the very grammar of modern physics, the corpuscular theory of light offered a clean and elegant solution. He imagined light as composed of tiny particles, corpuscles, that shot forth from luminous bodies like the sun, like fire, like stars. These corpuscles traveled in straight lines until they met surfaces, where they could reflect like billiard balls striking a table or refract as they entered denser media. This model explained why shadows were sharp, why light seemed to move so directly, and why it obeyed the rules of geometry when bouncing or bending. To Newton, the universe was already one vast system of particles and forces, planets orbiting under gravity's pull, apples falling to Earth in arcs determined by invisible laws. Why should light not belong to the same mechanistic vision? Newton's corpuscular theory fit neatly with the observations of his time, and his immense reputation gave it enormous weight. For decades, many scientists spoke of light as particles simply because Newton had said so. Waves, like those imagined by Huygens, felt softer, less tangible, harder to grasp in a world where mechanics reigned supreme. The idea of invisible oscillations rippling through an invisible ether seemed too speculative, too strange. Particles, however, were straightforward. They could be imagined, pictured, treated as little bodies of their own. The world was a cosmos of matter in motion, and light, too, could be tamed within that picture. But as the centuries unfolded, the cracks in this view grew wider. Experiments like Thomas Young's double slit in 1801 and Fresnel's work on interference and diffraction made the wave picture unavoidable. Still, the question never fully settled. If light was only waves, Then why did it sometimes behave as if it came in discrete packets? Why did its energy not spread continuously, but instead arrive in jumps, in bursts, in quanta that refused to be divided? The 19th century was dominated by the success of the wave model, yet beneath its triumph, hints of something else waited. The decisive shift came not from philosophers but from experiments with heat and radiation. By the end of the 19th century, scientists studying black-body radiation, a problem of how objects emit light when heated, ran into a paradox. Classical physics predicted that a hot body should emit infinite energy at short wavelengths, an absurd conclusion later nicknamed the ultraviolet catastrophe. Clearly, something in the wave model was missing. It was Max Planck in 1900 who introduced the idea that energy was not continuous but came in discrete packets, quanta. He did it reluctantly, more as a mathematical trick to make the equations work, but that trick cracked open a door that would transform physics forever. Planck suggested that light energy was quantized, arriving not as an endless stream but as bundles, as particles of radiance. This concept paved the way for Albert Einstein, who in 1905 went further. To explain the photoelectric effect, the way light could knock electrons out of metal surfaces, Einstein argued that light was made of quanta of energy, later called photons. These photons behaved like particles, each carrying a discrete chunk of energy proportional to its frequency. Waves could not explain why increasing the intensity of light sometimes did nothing, while increasing its frequency suddenly ejected electrons with ease. Particles could. The photon was born, and with it, the idea that light had a corpuscular side after all. Einstein's proposal was radical. To many, it seemed like a retreat back to Newton's corpuscles, an abandonment of the wave triumph that had explained so much. Yet experiments confirmed him. The photoelectric effect revealed the graininess of light, the way it came in packets rather than in a smooth flow. Photomultiplier tubes, detectors, and later technologies all showed the same thing. Light behaved as though it were composed of individual particles, quanta of radiance traveling through space. And yet, those same photons interfered like waves, diffracted like ripples, spread out like oscillations. Light refused to choose. This paradox became the foundation of quantum physics. Light was not merely particle or wave, but somehow both, its nature slipping beyond the categories that human language provided. At times it showed itself as a corpuscle, at other times as a wave, and sometimes as something even stranger, neither one nor the other, but a blend, a superposition. The double slit experiment, revisited with individual photons, confirmed the enigma. Send photons through the slits one at a time, and they still create an interference pattern, as though each photon were somehow a wave interfering with itself, spreading through both slits at once. Observe them closely, however, and they collapse into particles, striking one spot on the screen. Wave and particle, both and neither. This duality unsettled even Einstein, who gave the world the photon, but remained skeptical of the deeper implications of quantum mechanics. He sought a clearer picture, a deeper order beneath the apparent randomness. God does not play dice, he famously remarked, pushing back against the notion that light and matter behaved in fundamentally probabilistic ways. Yet the experiments refused to yield. The more carefully physicists looked, the more light behaved like something irreducible, beyond the reach of classical categories. To call photons particles is almost misleading. They have no rest mass, no size, no shape in the ordinary sense. They are excitations of the electromagnetic field, quantized disturbances that behave like particles only when interacting with matter. They carry momentum, they exert pressure, they can collide and scatter, and yet they also spread out, diffract, interfere, and vanish into pure energy. A photon is not a ball of light flying through space, but a quantum packet, a marriage of wave and particle that defies ordinary intuition. The particle vision of light reshaped not only physics but technology. Without it, solar panels would be impossible, for they rely on photons striking semiconductors and freeing electrons. Without it, lasers could not exist, for they depend on photons stimulating the emission of identical photons in perfect synchrony. Photomultipliers, fiber optics, quantum communication, all rest on the recognition that light is made of quanta. Every time a digital camera captures an image, every time a telescope records a distant galaxy, it is counting photons, particles of radiance that have traveled across space. The history of light as particles is also a history of humility. Newton's corpuscles explained some things, but not others. Einstein's photons explained more, yet still left questions unresolved. How can photons have no mass and yet carry energy? How can something behave both as a particle and as a wave? How does a single photon decide where to land or through which slit to pass until an observer looks? These questions stretch beyond science into philosophy, into the very way humans attempt to know reality. And there is something poetic in it too. To imagine that every glimmer of light, every sunrise and every candle flame is made of countless photons rushing outward at the speed of light. Each photon, a quantum of energy born in fire, star or lamp, traveling across space until it meets an eye, a leaf, a mirror, a detector. Each one indivisible, untouchable, a particle of radiance carrying the memory of its origin. The universe is full of them, streaming endlessly, filling every moment of vision, every patch of sky. At the same time, the photon remains elusive. Unlike particles of matter, it cannot be at rest. It cannot be bottled or pinned down. It exists only in motion, forever bound to its speed, forever light itself. This makes it both real and ghostly, tangible in its effects but intangible in its essence. A particle that is not a particle, a wave that is not quite a wave, a thing that slips between categories as if to remind us that reality is not built for human comfort. As the 20th century advanced, the photon became a cornerstone of quantum electrodynamics, the most precise theory in physics. It allowed scientists to predict interactions between light and matter with astonishing accuracy, down to decimal places that agree with experiments to 1 part in a trillion. Yet the mystery of its dual nature persisted, like a shadow behind the equations. Even now, when physicists speak of photons, they speak with a kind of reverence, acknowledging both their practical utility and their conceptual strangeness. The journey from Newton's corpuscles to Einstein's quanta is a reminder that science is not a straight line, but a dialogue across centuries. Newton saw light as particles and was partly right. Huygens and Young saw waves and were partly right. Einstein fused the two and was partly right. Each theory opened doors, explained phenomena, built technologies, and yet left the deeper essence of light still veiled. The photon is both an answer and a riddle, a particle of radiance that shines not only across space but across human thought, illuminating the limits of our understanding. Perhaps that is why light continues to captivate, not only as a physical phenomenon but as a symbol. It stands at the intersection of clarity and mystery, of what we know and what remains beyond us. To call it particles of radiance is to acknowledge one face of its nature, the way it arrives in discrete sparks, each carrying energy. But to live in the presence of light is to accept that those sparks are also waves, also fields, also something more. It is to walk daily in the glow of a paradox, bathed in photons that refuse to be fully explained, yet define everything we see. Light has always carried with it an almost mischievous quality, as though it delights in confusing the very minds that try to pin it down. For centuries, the argument had swung between two poles, waves or particles, oscillations through some invisible medium, or corpuscles launched like sparks from a flame. But in the 20th century, the experiments grew sharper, and the riddles they revealed were stranger than anyone could have expected. It was no longer a question of choosing wave or particle. Instead, the unsettling truth was that light seemed to be both, changing its mask depending on how you tried to look at it. This strange duality became one of the deepest mysteries in physics, and one of the most haunting puzzles of human thought. The experiment that makes the riddle clearest is deceptively simple. Two narrow slits cut into a barrier, a screen placed behind them, and a source of light directed toward the slits. When this setup was tested in the early 1800s by Thomas Young, the results shook science. If light were made of tiny particles, one would expect the photons, or corpuscles, as Newton would have called them, to pass through either one slit or the other, striking the screen in two bright bands. Instead, what appeared was an interference pattern, a series of alternating bright and dark fringes as though waves of light passing through both slits at once overlapped, combining in some places and cancelling out in others. This was the wave's signature written in brightness and shadow. For decades, the double-slit experiment seemed to settle the question. Light had to be a wave. Only waves produced interference. Only ripples could dance together in this way. The fringes were undeniable, mathematical fingerprints of oscillation. And yet, as technology advanced, the picture grew more perplexing. When detectors became sensitive enough to emit only one photon at a time, physicists repeated the experiment, sending individual particles of light toward the slits. Logic suggested that if only one photon traveled at a time, there could be no interference, no second photon to interfere with. But the interference pattern still appeared, gradually building up as though each solitary photon were interfering with itself, traveling through both slits at once like a ghostly probability wave. This is where the dance of duality reveals itself most starkly. Each photon arrives at the screen as a tiny localized impact, a dot, a particle, undeniable. Yet as the impacts accumulate, they trace out the interference fringes of a wave. Light is both a spray of bullets and a ripple on a pond, a dual reality stitched together in a way no classical picture can explain. The language of physics shifted, adopting probability as its grammar. Photons do not travel like billiard balls or like ripples exactly, but like waves of possibility. They spread out, explore multiple paths, pass through both slits until a measurement is made. Then, with a kind of ruthless decisiveness, the photon appears in one place, a single dot on the screen, collapsing the wave into a particle. To many, this collapse is the strangest step in the dance. Before observation, light behaves as though it is everywhere at once, both slits open to its passage, both paths taken simultaneously. After observation, it is nailed down, reduced to a single point. It is as though the universe itself waits to see what humans will do, as though reality is not entirely fixed until it is watched. This notion disturbed Einstein profoundly, who resisted the idea that observation could influence reality. He quipped that the moon does not cease to exist when no one looks at it. Yet quantum mechanics seem to insist that, at least for light and particles at the smallest scales, observation and existence were intertwined. The double-slit experiment became more than a demonstration. It became a parable of modern physics. Every time it was repeated with refinements, using electrons instead of photons, using neutrons, even molecules thousands of times heavier than atoms, the result was the same. The interference pattern persisted, evidence that the world at its most basic level is ruled not by certainty, but by probability waves. The dance between particle and wave is not a flaw of light, but its nature. And it is not only light. Matter itself, solid atoms, tangible electrons, shares in this duality, rippling through probability waves, collapsing into particles when observed. This revelation unsettled the very foundations of physics. Classical mechanics had promised a world of clarity. particles with definite positions, moving on predictable paths. The wave picture had promised continuity, oscillations spreading through space, smooth and deterministic. But light's duality revealed a world where certainty dissolved into possibility, where the categories themselves, wave or particle, were inadequate. Light was not switching costumes between the two. It was both at once, a phenomenon that forced scientists to invent entirely new mathematics, quantum mechanics, to describe it. The strange dance also raised questions that touched philosophy as much as science. What counts as observation? Does a photon decide its path only when a conscious observer sees it? Or is the collapse triggered by any interaction with matter? If a photon leaves a star millions of years away, does it travel as a probability wave across the cosmos, choosing its path only when it meets a telescope's mirror or a human retina? These questions gave rise to entire schools of interpretation: Copenhagen, many worlds, pilot wave, all attempts to make sense of the same stubborn experiment. None fully resolve the strangeness. All admit that light's duality is beyond ordinary intuition. And yet, in its refusal to be pinned down, light opened doors to technology as strange as its own behavior. The principles of quantum mechanics birthed lasers, semiconductors, fiber optics, quantum cryptography. The same photons that baffle our categories now stream through the internet's cables, secure financial transactions, and read barcodes at the grocery store. The duality that once seemed a flaw became a resource, a foundation of the modern world. To study light's ambiguity was to learn how to harness it, even if its essence remained elusive. There is a poetic side to this too. Imagine a photon traveling through space, a packet of energy born in the heart of a star or the filament of a bulb. It spreads like a wave, considering every path, filling the room with probability. It drifts toward two open slits, and in that moment it is everywhere, through the left, through the right, through both at once. Only when it meets the screen, or your eye, or a detector, does it make its choice. The wave collapses into a point, a single spark of radiance. Multiply this by trillions, and the whole visible world is built. Beams of sunlight, flickers of fire, the glow of cities, all constructed from particles that refuse to stop being waves. This duality is not a problem to be solved, but a reality to be accepted. Science names it wave-particle duality, a phrase that captures the paradox but cannot explain it. Even now, a century after its discovery, no one can say what light really is. Is it waves pretending to be particles, or particles pretending to be waves, or something deeper that is neither and both? The mathematics works, the predictions are exact, the technologies flourish, yet the essence remains veiled, reminding us that the universe is not obliged to fit human categories. The duality's strange dance humbles and inspires. It shows that the universe is subtler than logic, more mysterious than the brightest intellects had imagined. Newton saw corpuscles, Huygens saw waves, Einstein saw photons, Young saw interference, and all were right, yet incomplete. Light wears both masks, never choosing, never surrendering its secret. Every candle flame, every sunrise, every photon striking your eye as you read is part of that eternal performance. The paradox that illuminates the world while concealing its own truth. In the 19th century, the world of science seemed on the edge of completion. Newton's laws had explained the motion of planets and apples with mathematical precision. Maxwell's equations had woven electricity and magnetism into a grand symphony, revealing light itself as an electromagnetic wave. It felt as though the universe were finally being written down in full sentences, each equation another line of cosmic poetry. But there was still one loose thread, a small but stubborn question that refused to be tucked away. If light is a wave, then what is waving? All waves known to humanity needed a medium. Sound required air, ripples demanded water, Vibrations shook through solids. Surely light too must travel through some invisible substance, an all-pervading medium that carried its ripples across space. This hypothetical medium was given a name both haunting and hopeful: the ether. The ether was imagined as the silent stage on which the universe played its dramas. It was everywhere and nowhere, filling the void between stars, surrounding the earth, penetrating every material object without resistance. It had to be perfectly transparent, perfectly elastic, and yet so subtle that it escaped every attempt to touch or weigh it. For physicists of the 19th century, the ether was not a question, but a necessity. Without it, light had no foundation. Waves, after all, cannot ripple through emptiness. The ether, in their minds, was the hidden fabric of reality. This invisible sea became more than a scientific proposal. It was a philosophical comfort. The ether offered a way to imagine the cosmos as unified and continuous. No longer was empty space a void. It was a vast ocean of substance, a medium that tied together the planets, the stars, and the very beams of starlight striking human eyes. Scientists debated its properties endlessly. Some thought it must be rigid to carry transverse waves like those of light. Others argued it had to be fluid to avoid resisting the motion of planets. It was a paradoxical substance, solid yet intangible, strong yet undetectable. But to most physicists, the ether was as real as the air in their lungs, even if it remained elusive to experiment. The search for evidence of the ether became a scientific obsession. If Earth drifted through this cosmic ocean, then the speed of light measured in one direction should differ slightly from that measured in another, depending on whether the planet was moving with or against the flow of the ether. It was the same principle sailors used when measuring currents. Just as a boat moves faster downstream than upstream, light should move faster or slower, depending on the ether wind. The challenge was to build an experiment delicate enough to measure the difference. In the 1880s, two American physicists, Albert Michelson and Edward Morley, took up that challenge. Michelson, already famous for his precision instruments, designed an apparatus so sensitive it could detect differences in the speed of light smaller than 1 part in 100 million. His device, the Michelson interferometer, split a beam of light into 2 paths at right angles. The beams traveled different routes, bounced off mirrors, and then recombined. If Earth was moving through the ether, one beam would be slightly slowed by the ether wind, while the other was unaffected. When the beams met again, they would be out of step, producing a measurable shift in the interference pattern. The interferometer was a kind of cosmic wind vane designed to catch the invisible current of the ether. They expected results. In fact, Michelson predicted precisely how much the interference pattern should shift as the Earth's motion carried it through the ether at different times of day and year. The experiment was repeated in Cleveland, in Berlin, in observatories across the globe. Each time, scientists prepared themselves to finally trap the ghost. Yet what they found was silence. The interference fringes stayed stubbornly in place, no matter the hour, no matter the season, no matter the orientation of the device. The expected shift did not appear. The result was always the same: nothing. The Michelson-Morley experiment is often called the most famous failed experiment in history. Its failure was not a flaw, but a revelation. For if the ether truly existed, it should have revealed itself in those delicate shifts of light. Its absence was a profound shock. The experiment suggested that the speed of light was the same in every direction, unaffected by motion through any medium. It suggested that perhaps there was no ether at all. The cosmic ocean vanished like mist in sunlight. At first, many scientists resisted. The ether had been too comfortable, too necessary a concept to abandon overnight. Alternative theories sprouted like weeds in a garden. Some argued that the ether was dragged along by the Earth, clinging invisibly to the planet and canceling out the expected shifts. Others proposed strange contractions of matter, where moving objects shrank imperceptibly in the direction of motion, balancing the books of the experiment. Each theory tried to save the ether from extinction, preserving it against the evidence. Yet with each passing year, the ghost grew harder to defend. The absence of the ether forced a new way of thinking about light. If light required no medium, then it traveled through the vacuum of space in a way unlike any other wave known to humans. This implied that the universe was stranger than classical physics had imagined, a place where emptiness was not empty, but still carried structure. It was Albert Einstein who took the boldest step. In 1905, he proposed his theory of special relativity, declaring that the speed of light was a constant of nature, the same for all observers, regardless of their motion. In one stroke, the need for ether dissolved. Light did not ripple through a medium. It defined the structure of space-time itself. The shift was seismic. For centuries, humans had imagined themselves moving through a universal stage, whether the crystalline spheres of Aristotle or the ether of the 19th century. Relativity tore down the stage and revealed that there was no absolute background, no universal sea. Space and time themselves bent and flexed with motion, and light was their ruler, the unchanging speed that set the limits of causality. The Michelson-Morley experiment, with its stubborn null result, became the cornerstone of this revolution. Even so, the ghost of the ether lingered in the imagination. Some scientists continued to wonder if something like it might exist in new guises, hidden beneath the mathematics of quantum theory. The vacuum, after all, is not truly empty. Quantum field theory tells us that it seethes with fluctuations, virtual particles appearing and vanishing in an endless foam. In this sense, the modern vacuum carries a faint echo of the old ether, not as a mechanical medium through which light ripples, but as a restless field of potential, a background from which particles and waves emerge. The dream of an underlying fabric did not vanish entirely, it transformed. The story of the ether is a reminder that science is not just a march of progress but a dance of ideas, some clung to long after their usefulness fades. The ether was beautiful, intuitive, comforting. It made sense to the human mind, which struggles to imagine waves without water or sound without air. Yet the universe does not always cater to intuition. It demands that humans adjust their imaginations, bend their categories, and sometimes let go of what feels natural. The ghost called ether teaches humility. Even the most elegant ideas can dissolve in the light of evidence. Picture, for a moment, the 19th century scientists peering into the eyepiece of Michelson's interferometer. They expected to see the fringes of light shift, proof of the invisible ocean carrying the cosmos. Instead, they saw stillness, an unbroken pattern, the refusal of the universe to comply with human expectation. That silence was more eloquent than any measurement. It told of a cosmos stranger than oceans and currents, stranger than rigid mediums filling the void. It whispered of relativity waiting on the horizon, of a future where light would not ride a wave but define the structure of existence itself. Today, when satellites beam signals across space, or when telescopes catch light from galaxies billions of years away, they do so with the knowledge that no ether carries those photons. They cross the vacuum directly, born not by substance but by the structure of space-time itself. The ghost is gone, but its absence continues to shape the way we think, a shadow that lingers as a reminder of how bold science must be to let go of its most cherished ideas. The ether was a dream, and its undoing was a shock. Yet from that shock grew one of the greatest revolutions in human understanding. In abandoning the ocean of nothingness, physics gained a universe alive with relativity, a cosmos where the constant speed of light anchors reality. The ghost called ether may have faded, but the questions it raised about what carries light, what fills the void, what the true fabric of reality is, remain as haunting as ever. For even without the ether, light has not yielded its secrets. It shines, it dazzles, it carries energy across impossible distances. And still, at its core, it slips through our grasp, reminding us that every discovery is only another step into mystery. James Clerk Maxwell never set out to change the very way humanity saw light. He began instead with a fascination for electricity and magnetism, forces that in the early 19th century seemed like cousins who resembled each other faintly but belonged to different families. Sparks could leap across wires, magnets could pull iron, coils could induce currents, but no one understood how all these puzzle pieces fit together. Some believed electricity was a kind of fluid that flowed through wires, while magnetism was a completely separate property of certain materials. Others thought they might be related, but could not describe how. Into this maze stepped Maxwell, armed with mathematics, patience, and a vision that would prove transformative. In the 1860s, he published a set of equations that brought unity where there had been confusion. These equations, compact and elegant, revealed that electricity and magnetism were not two forces, but one, bound together in the fabric of fields. A moving electric charge created a magnetic field. A changing magnetic field created an electric field. They were two faces of the same coin, locked in eternal exchange. To describe them properly, Maxwell invented the concept of fields not just as abstractions but as real, physical presences that filled space. Suddenly, empty space was not empty at all. It hummed with invisible lines of force stretching from charge to charge, curling around currents, linking every spark and magnet in the universe. It was while working through the consequences of his equations that Maxwell stumbled on something extraordinary. If changing electric and magnetic fields generated one another, then together they could propagate through space, self-sustaining like partners in a dance. What would such a wave look like? Maxwell calculated its speed using the constants in his equations, numbers measured in experiments with electric charges and magnetic fields. The result startled him. The speed matched precisely the measured speed of light. In that moment, a thunderclap echoed through science. Light itself was revealed to be an electromagnetic wave. This revelation meant that the familiar glow of a candle, the golden warmth of the sun, and the silent beams that traveled across empty space were not mysterious rays or streams of particles, but ripples in an invisible field. Light was electricity and magnetism in motion, woven together into waves that could cross the void. Suddenly, phenomena that had seemed separate, the spark in a telegraph wire, the pull of a compass needle, and the twinkle of a star, were chapters of the same story. Maxwell's equations had achieved a unification that still inspires awe. Two forces understood as one, their marriage producing light. The impact was immense. Maxwell's work gave humanity not only a deeper understanding of nature, but also a toolkit for technology. The realization that light was electromagnetic suggested that other waves might exist beyond the narrow band visible to human eyes. Infrared, ultraviolet, radio, and X-rays, all were born from this insight, and all were later discovered. The world changed accordingly. Radio carried voices across continents, microwaves heated food, X-rays revealed bones hidden beneath skin. The electromagnetic spectrum expanded human senses far beyond evolution's design. All of it flowed from the clarity Maxwell's equations provided. Yet for all their power, the equations did not settle every question. They described beautifully how electromagnetic waves moved, how charges and currents produced fields, and how fields interacted with matter. But they did not say why. They assumed the existence of charges and fields as starting points, not things explained from deeper principles, nor did they address the underlying mystery of what a field actually was. Was it a physical substance stretching through space like the discarded idea of the ether? Was it a purely mathematical convenience? Maxwell himself sometimes spoke of the ether when discussing fields, as if reluctant to abandon entirely the idea of a medium. His mathematics worked perfectly whether or not such a medium existed, leaving the philosophical question unresolved. Another problem arose from the clash between Maxwell's theory and Newtonian mechanics. In Newton's universe, speeds were relative. A moving observer and a stationary one might measure different velocities for the same object. Yet Maxwell's equations implied that the speed of light was fixed. No matter how you moved, the math said light should always travel at the same rate. This inconsistency gnawed at physicists who tried to reconcile the contradiction with theories of ether drift or hidden corrections. It was not until Einstein's theory of relativity in 1905 that the tension was resolved, revealing that space and time themselves bent to ensure the constancy of light. In this sense, Maxwell's equations prepared the stage for relativity by posing a problem too stubborn to ignore. Still, what Maxwell accomplished was staggering. He took invisible, intangible forces and turned them into a coherent story written in mathematics. His 4 equations are compact enough to fit on a single page, yet vast enough to explain everything from why a magnet sticks to a refrigerator to how the sun's rays warm the earth. They show that the dance of electricity and magnetism is not just a curiosity, but the foundation of modern life. Every radio signal, every Wi-Fi connection, every beam of light pouring through a window is Maxwell's legacy in action. The elegance of his work also helped shape the philosophy of science itself. The idea that nature's complexity could be reduced to a few simple equations became a guiding dream for physicists. Maxwell's success inspired later generations to search for unification at ever deeper levels, uniting electricity with magnetism, then uniting them with the weak nuclear force, and eventually seeking a single theory that might embrace all the forces of nature. His equations were not just discoveries, but a demonstration of what science could aspire to: simplicity beneath complexity, harmony beneath apparent chaos. And yet beneath this harmony lies unresolved strangeness. Light is electromagnetic radiation, yes, but its dual nature as both wave and particle remains unsettled in human understanding. Maxwell's equations do not explain why light sometimes behaves like a ripple and sometimes like a stream of quanta. They do not account for the quantum leaps of energy that photons obey, or the uncertainty that seems to haunt light at its smallest scales. The equations stand as a monumental achievement, but also as a doorway into further mysteries. They solved so much, but not all. Imagine yourself in the 19th century, living in a world lit by gas lamps, travelled by horse-drawn carriages, and connected by telegraph wires. Then imagine learning that the light of those lamps, the glow of the sun, the invisible force turning a compass needle, and the crackle of a telegraph line are all manifestations of the same phenomenon. The very fabric of your world has been redefined. That was the power of Maxwell's insight, and even today, more than a century later, we live in its glow. When you pick up a phone and send a message across the globe, when you lie on the beach feeling the sun's warmth, when you switch on a light and fill a room with illumination, you are living in a universe Maxwell helped reveal. His equations are not abstract relics but the heartbeat of modern life, and still, they are incomplete in one profound sense. They do not explain why light exists in the form it does, why it carries both wave and particle traits, or why it refuses to yield fully to human categories. They tell us how light moves, but not why it shines. This tension between clarity and mystery is the essence of the story of light. Maxwell pulled back the curtain, revealing its electromagnetic nature, yet in doing so he exposed new puzzles that remain unsolved. Light is both explained and unexplained, both familiar and alien, and it is this dual quality that keeps scientists, philosophers, and dreamers returning to its study. Each explanation reveals more layers, more questions, more wonder. Maxwell's equations stand today as monuments carved into the intellectual landscape of science. They are precise, predictive, and endlessly useful. They show us that light is not merely a physical presence, but a unifying principle, the thread that ties electricity and magnetism into a single fabric. But beyond their utility, they remind us that even the most elegant answers can open doors to deeper mysteries. Light, the traveler of the cosmos, remains as elusive in essence as it was to the first humans who gazed at fire. The equations describe its steps, but the dance itself remains mysterious. And so, the journey continues. From Newton's prism to Maxwell's equations, humanity has learned much about light, but never everything. The equations that knit electricity and magnetism into waves gave us radio, television, lasers, and the modern world itself, but they did not give us closure. They gave us instead an invitation to keep asking, to keep wondering, to keep chasing the elusive essence of light across the centuries. At the turn of the 20th century, physics was basking in its own confidence. Maxwell's equations had brought electricity and magnetism into a grand unity. Newton's laws of motion still ruled the movements of planets and pendulums. Thermodynamics described heat, engines, and entropy. To many scholars of the time, the natural world looked almost fully charted. A few stubborn problems remained: puzzles of heat radiation, oddities in atomic spectra. But these were expected to yield with a little clever mathematics, perhaps the tightening of a formula here, the adjustment of an assumption there. What no one expected was that those small cracks would widen into chasms, tearing open the foundations of classical physics and giving birth to an entirely new way of understanding light and energy. One of the cracks was called the ultraviolet catastrophe. Scientists studying how objects radiate heat, glowing iron bars, hot ovens, the stars themselves, were puzzled by the distribution of light these objects emitted. At lower frequencies, their predictions matched experiment nicely. But at higher frequencies, the mathematics of classical physics demanded that a heated object should radiate infinite amounts of energy. This was absurd. No laboratory, no star, no furnace produced such a runaway spectrum. The laws that worked so well at ordinary scales collapsed in the high-frequency realm. It was as though nature herself refused to follow the rules humans had written for her. Into this problem stepped Max Planck, a German physicist of meticulous character, who in 1900 proposed a desperate, almost reluctant idea. To resolve the paradox, he treated energy not as a smooth, continuous quantity, but as something delivered in discrete packets, what he called quanta. According to Planck, the energy of light at a given frequency could only exist in multiples of a tiny unit, E equals h nu, where h was a constant he introduced, and nu the frequency. This constant, Planck's constant, was unimaginably small, but it changed everything. At first, Planck himself considered it a mathematical trick, a convenient assumption to save the theory rather than a revelation about reality. Yet the trick worked. With quanta, the predictions matched the observed spectra of heated objects perfectly. The catastrophe was avoided. What Planck had stumbled upon was not a patch, but a portal, though he did not fully realize it. He had introduced discreteness into physics, suggesting that light and energy came in packets, not smooth waves. The idea was radical, uncomfortable, almost heretical to a culture of science steeped in continuity. And yet, within a few short years, it would grow into the foundation of quantum theory. The next step came from Albert Einstein in 1905, a year that would cement his place among the greatest thinkers of all time. Among the many papers he wrote that year was one on the photoelectric effect, a strange phenomenon in which light shining on a metal surface caused electrons to leap free. Classical wave theory predicted that the effect should depend on the intensity of light. The brighter the beam, the more energy it carried, and the more electrons it should dislodge. But experiments showed something baffling. dim light of high frequency could release electrons instantly, while bright light of low frequency sometimes had no effect at all. Einstein's explanation was bold. He argued that light itself was made of quanta, later called photons. Each photon carried an energy determined by Planck's relation, E equals h nu. Only photons with sufficient energy could knock an electron loose, regardless of brightness. Thus, a dim ultraviolet beam could succeed where a blazing red beam failed. This was not just a mathematical trick. This was a claim about reality. Light was not merely a wave. It was a shower of particles. The implications were staggering. For centuries, the debate over the nature of light had swung between waves and particles, with experiments seeming to favor one or the other. Newton's corpuscles gave way to Huygens waves, Young's slits to Maxwell's fields. Now, Einstein declared, light was both, an electromagnetic wave described by Maxwell, but also a stream of photons, discrete packets of energy. The ancient argument was resolved, but only by embracing contradiction. Light was a dual citizen of two worlds, refusing to be contained in one identity. Einstein's photoelectric paper earned him the Nobel Prize in 1921, not his relativity work, which at first seemed too wild for many physicists. It was this paper that convinced the world that light had a quantum character, that energy arrived in packets. The photoelectric effect also paved the way for modern technologies. Solar panels, digital cameras, photodiodes, all descendants of Einstein's insight that light comes in photons. But the quantum revolution did not stop there. Once the idea of quanta entered physics, it spread like wildfire. Atoms, once imagined as miniature solar systems with electrons orbiting nuclei like planets around the sun, refused to obey classical rules. Classical physics could not explain why electrons didn't spiral inward, radiating energy until atoms collapsed. Nor could it explain why atoms emitted light at only certain discrete frequencies, producing spectral lines like barcodes for each element. Enter Niels Bohr, who in 1913 proposed a new model of the atom. He borrowed Planck's quantum idea and applied it to electron orbits, declaring that electrons could occupy only certain quantized levels of energy. They could leap from one level to another, emitting or absorbing a photon whose energy matched the difference, but they could not hover in between. This explained the spectral lines beautifully. Atoms emitted light in quanta because electrons shifted in quanta. The atom was no longer a smooth mechanical system, but a quantum staircase of discrete steps. As more evidence accumulated, the quantum world grew stranger. Light, it seemed, was both a wave and a particle. Matter, too, was caught in the dance. Louis de Broglie proposed in the 1920s that electrons could behave like waves, producing interference patterns much like light. Experiments confirmed it. The duality spread. If light could be particle and wave, so could matter. From these revelations emerged the full flowering of quantum mechanics, Schrödinger's wave functions, Heisenberg's uncertainty, Dirac's relativistic equations. But at the root of it all lay the birth of quantum light, the realization that energy itself came in indivisible packets, and that the glow of the universe was not a continuous flood, but a rain of photons. The philosophical shock cannot be overstated. Classical physics imagined a universe of smooth causality, where forces acted continuously, where energy flowed like water. Quantum physics revealed a world of discreteness, leaps, and probabilities. Light, the most ancient companion of humanity, turned out to be not what it seemed. The candle's flame, the sun's rays, the starlight crossing vast gulfs of space, all were composed of countless tiny quanta, each with a fixed energy, each behaving sometimes like a particle, sometimes like a wave. And still, questions multiplied. What exactly is a photon? Is it a particle, a packet, a disturbance in a field? Why does it sometimes spread like a wave, only to land with pinpoint precision like a bullet? How does it know when to reveal which face? Quantum mechanics describe these behaviors with extraordinary accuracy, predicting experimental results to many decimal places. But description is not explanation. The essence of light remained elusive. The practical consequences, however, were undeniable. Out of quantum light came lasers, devices that harnessed the coherence of photons to produce beams of perfect brightness. Out of quantum light came quantum electrodynamics, the most precise theory in science, capable of predicting the magnetic moment of the electron to 1 part in a trillion. Out of quantum light came technologies that shape modern life. Semiconductors, LEDs, fiber optics, quantum computers on the horizon. The very fabric of our technological civilization is woven from photons, the quanta first glimpsed by Planck and Einstein. And yet, when you look up at the night sky, when you trace the shimmer of moonlight on water or watch sunlight fracture into rainbows, the mystery remains palpable. These photons, born in the heart of atoms, cross vast spaces to strike your eyes, delivering packets of energy that create vision itself. You are seeing quanta. You are experiencing Planck's revolution every time you open your eyes. The birth of quantum light was not a simple correction to old ideas. It was a rupture, a redefinition, a humbling. It told humanity that the universe is not continuous but granular, not fully knowable but governed by probabilities, not mechanical but quantum. Light became not just illumination but revelation, a reminder that the world is stranger than common sense, richer than classical certainty, and more mysterious than any equation can capture. And so, the story of light grew deeper. From Newton's prism to Maxwell's waves to Planck's quanta and Einstein's photons, each step brought clarity and confusion in equal measure. Light was explained, but never fully. Each discovery revealed more wonder, more paradox, more questions that refuse easy answers. The birth of quantum light was not an ending but a beginning, a doorway into the strangest and most fruitful era of physics, one that still shapes our understanding of the cosmos and our place within it. Imagine standing in a quiet laboratory where the hum of equipment blends with the nervous excitement of history in the making. Before you is not some massive machine of colliding particles or space-age electronics, but something disarmingly simple, a screen, a barrier, and a light source. It is the kind of setup a child could sketch, almost laughably basic compared to the grand ambitions of science. And yet, in its simplicity, it hides one of the most disturbing puzzles ever uncovered. This is the double-slit experiment, the nightmare that refuses to leave physics alone, a riddle so sharp it slices into our understanding of reality itself. Begin with the basics. Imagine light as a wave, rippling across space the way water ripples across a pond. If you shine that wave through 2 narrow slits cut side by side in a barrier, each slit acts like a new source of ripples. As the waves spread out, they overlap. Where the peaks of one wave meet the peaks of another, they reinforce into brightness. Where the peaks meet troughs, they cancel into darkness. On the screen behind the slits, the result is a banded pattern of light and dark, called interference fringes, the unmistakable fingerprint of a wave. Now imagine light as a particle, a tiny corpuscle or photon flying like a bullet. If light is really made of these particles, you might expect each one to pass through either the left slit or the right slit. 2 slits should mean 2 clusters on the screen, a simple double shadow. That is what particle logic demands. No ripples, no interference, just bullets hitting targets. But here is the problem. When scientists actually performed this experiment, starting with Thomas Young in the early 19th century, they didn't get 2 neat clusters. They got the interference pattern. Light spread out, overlapped, and painted the screen with alternating bright and dark stripes. Waves, not bullets. The conclusion seemed obvious. Light was a wave. The nightmare, however, began when technology grew sensitive enough to dim the source, to let light trickle out not in torrents but in single photons, one at a time. If photons were truly particles, each one should hit the screen independently, producing random dots, eventually building up two clusters behind the slits. But when scientists ran this careful version of the experiment, the strangest thing happened. Even with photons fired individually, with no neighbors to interfere with, the interference pattern still emerged over time. Each photon seemed to interfere with itself, as though it passed through both slits at once. This is the puzzle that makes students shake their heads and professors grow quiet. A photon is a particle because it strikes the screen as a single point, but it is also a wave because over many repetitions the interference pattern emerges. The same entity plays two contradictory roles depending on how we look at it. Light refuses to choose, refuses to fit into the neat categories of classical thought. The nightmare deepens when you try to catch the photon in the act. Suppose you place detectors at the slits, tiny instruments designed to record which slit the photon passes through. Surely this will settle the question, left slit or right slit. But here, reality plays its cruelest trick. The moment you measure, the interference pattern disappears. Instead of stripes of brightness and darkness, you get the particle pattern, two neat clusters, as if the photon has been forced to commit to one slit or the other. The act of measurement changes the outcome. Observation itself reshapes reality. This is not a parlor trick or a laboratory fluke. It has been repeated countless times with photons, with electrons, even with larger particles like molecules. Every time, the result is the same. When you look to see which path the particle takes, the interference vanishes. When you refrain, the interference returns. The universe seems to care whether it is being watched. What does this mean? That question has haunted physicists for over a century. Some interpretations say that the wave represents probability, a mathematical description of where the photon might be found. Until measured, the photon is not in one place, but in many, smeared out across possibilities. Observation collapses the wave, forcing the photon to choose. Others argue that the photon splits into multiple realities, each path taken in a separate branch of the universe, with interference arising from this invisible multiverse. Still others take a more pragmatic stance, saying the mathematics works, the predictions are precise, and perhaps meaning itself is a question too human for quantum mechanics. Whatever the interpretation, the double-slit experiment leaves no one comfortable. It denies us the certainty we crave. In the classical world, things are either here or there, wave or particle, left or right. In the quantum world, light exists in a haze of potential, both here and there, both wave and particle, until our act of looking pins it down. Reality, it seems, is not fully real until observed. Consider the implications beyond the laboratory. The very screen you are looking at, the neurons firing in your brain, the sunlight crossing the void from the stars, all are carried by photons. Every act of vision, every flicker of flame, every glow of a city at night is composed of particles that refuse to decide what they are until forced. Your daily life is illuminated by contradictions. The experiment has grown even stranger with refinements. Physicists have tried variations with delayed choices, where the decision to measure or not is made after the photon has already passed the slits. Even then, the photon responds to the future measurement, producing or withholding interference as though time itself were pliable. They have built quantum erasers, where information about the photon's path is erased after the fact, and the interference pattern reappears as though the photon knew that its history had been wiped clean. Such results stretch not just our sense of physics, but our very sense of causality. And yet, in the middle of this nightmare, there is beauty. The double-slit experiment is not only a paradox, but also a window It reveals that the world is deeper and stranger than intuition allows. It teaches humility, showing that even with centuries of thought, humanity has only scratched the surface of reality. It points the way to technologies, quantum computing, quantum cryptography, that harness the strangeness rather than fight it. The same photons that baffle us in the lab are already being used to secure communications and build new forms of machines. Still, the mystery remains. What is light, really? A wave, a particle, a probability cloud, a flicker of multiverses? Every answer seems provisional, every definition incomplete. The double-slit experiment refuses closure. It sits in physics like a stone in a shoe, a constant reminder that our theories are tools, not truths, and that the universe is under no obligation to make sense according to human categories. When you think of light now, of a candle flame, of moonlight across water, of the gentle glow of a lamp in your room, you are seeing not just photons, but paradox. You're watching the world behave in a way that defies simple explanation. Light has guided humanity for millennia, but in its quantum dance, it still leads us into darkness. The double-slit nightmare is not just a scientific puzzle, it is a philosophical wound, a reminder that reality is stranger than our language can hold, and that perhaps the most dangerous question of all is the one asked by a beam of light passing through two slits. What am I? In the quiet precision of a laboratory, when a beam of light is carefully directed toward a screen, everything seems simple. A switch is thrown, the lamp hums, photons set sail, and the rules of optics appear ready to play out as textbooks promised. Yet nestled within this routine lies a secret that shakes the foundations of both science and philosophy. It is the unsettling fact that light behaves differently depending on whether or not we observe it. In the strange world of quantum mechanics, the act of measuring does not simply reveal reality, it changes it. This truth has become one of the most famous and most unnerving discoveries of modern physics. Imagine once more the double-slit experiment, that deceptively simple setup where light passes through two narrow slits before striking a screen. When no one checks which slit the photon takes, the interference pattern blooms in elegant stripes, the clear signature of waves interfering with themselves. But when detectors are installed to measure the path, the pattern vanishes. The photons line up as if they are merely particles, leaving two neat clusters. The only difference between these two outcomes is whether someone is watching. This is not metaphor, not poetry. It is empirical fact, verified countless times. Here is the strangeness. Observation is not supposed to carry such weight. In the classical world, the universe does not care whether anyone watches. A tree falls in a forest, and physics insists it makes a sound whether or not an ear is there to hear it. But in the quantum world, the act of observing seems to shape the very event being observed. Light behaves one way when ignored, another when checked upon. It is as though photons reserve their true form until forced to declare it under scrutiny. Scientists call this the observer effect, but naming it does not diminish its mystery. Some interpretations of quantum mechanics describe the photon's existence as a probability wave, a haze of potentialities. When unmeasured, the photon is not a point or a line, but a cloud of possibilities, simultaneously traveling through both slits. The act of measurement collapses that haze into a single outcome. Observation does not reveal reality, it selects one version from many. But this language only raises further questions. What counts as observation? Is it a human eye, with consciousness and intent? Is it a machine, clicking and whirring with no awareness of what it records? Is it simply any interaction with the environment, such as a photon bouncing off a particle of dust? Each answer carries consequences. If it is only interaction, then the universe continually collapses possibilities into facts all on its own. If it requires consciousness, then the human mind is somehow entangled with the laws of physics in a way we scarcely understand. The stakes become clearer with experiments that delay the act of observation. In one variation, physicists let photons pass through the slits and only afterward decide whether to measure their path. Strangely, the outcome still reflects the later choice. If the path is measured after the fact, the photons behave as particles. If it is not, the interference pattern reemerges. It is as though the photon's past behavior is retroactively decided by a future action. The universe in these tests does not appear to play by the rules of linear time. Quantum eraser experiments go further. In these setups, scientists measure the path of photons, but then erase the information before it can be known. When the data is erased, the interference returns, as though the universe knows that the information has been lost. It is a deeply unsettling discovery. What matters is not just the physical act of measurement, but whether the information about the measurement is preserved. Reality appears to care about knowledge itself, about the existence or absence of information. These results open a doorway into territory once reserved for philosophers. If observation changes reality, what role does consciousness play in the machinery of the cosmos? Is the mind not merely a bystander, but an actor woven into the quantum fabric? Could awareness itself be part of the universe's architecture, necessary for events to resolve from potential into fact? Such questions remain speculative, but they cannot be ignored when experiments repeatedly suggest that the boundary between observer and observed is blurred. It is important to remember that physicists do not agree on a single interpretation. The Copenhagen interpretation, famously associated with Niels Bohr, suggests that the wave function, a mathematical expression of probabilities, collapses upon measurement. The act of observation forces the universe to choose. The many worlds interpretation proposed by Hugh Everett takes a different approach. Every possible outcome actually occurs, but in branching universes. When you observe a photon, you see only one branch, while countless others unfold elsewhere. In this view, the interference pattern is the ghostly trace of those other realities. Other theories attempt to restore realism, arguing that the wave function does not collapse, but that hidden variables, yet undiscovered, determine the outcome. Still others place the burden on decoherence, the process by which quantum states interact with their environment and lose their delicate superpositions. Each explanation works in its own mathematical domain, but none resolves the feeling of strangeness. The experimental facts remain. Observation alters the game. The cultural resonance of this mystery has spilled far beyond physics. Writers, philosophers, and spiritual traditions have all seized upon the idea that consciousness and reality are intertwined. It is easy to see why. If photons defer their true nature until measured, does that mean reality itself is somehow participatory? Are we not just inhabitants of the cosmos, but co-creators of its unfolding? While many scientists caution against drawing such sweeping conclusions, the allure of the thought is undeniable. The laboratory with its wires and detectors begins to look like an oracle hinting at truths larger than science can contain. For the working physicist, however, the puzzle is not an invitation to mysticism, but a practical challenge. Quantum mechanics, despite its strangeness, is astonishingly successful in predicting outcomes. Every smartphone, every laser, every MRI machine depends on its rules. The equations work. Yet beneath this success lurks the unanswered question of why. Why does the photon wait for us to look? Why does information matter more than mechanics? Why does light refuse to reveal its nature until cornered? This paradox has practical consequences too. The observer effect underlies the emerging field of quantum computing. In such systems, information is stored not in simple bits of zeros and ones, but in qubits that exist in superpositions, many states at once. The challenge is that observation collapses these states prematurely. Engineers must carefully shield qubits from outside interference because the universe itself seems too eager to measure them. Without this delicate balance, the fragile quantum magic evaporates. Here, the nightmare of observation is not just philosophical, it is technical, the difference between a working quantum machine and a useless pile of circuits. Even outside laboratories, the echo of this truth lingers in daily life. When you look at a star, the photons that strike your eye may have traveled for millions of years. Their path through space, their identity as wave or particle, their very definition of reality, seems to crystallize only when absorbed into your retina. A quiet act of stargazing becomes part of the universe's decision-making process. The same photons could just as easily have passed you by, invisible and unresolved. But once observed, they are real. And so we arrive at a haunting possibility. Perhaps the cosmos is not a pre-written script, with every event fixed in advance, but an improvisation shaped by the act of watching. Perhaps reality is not a stage on which we are spectators, but a canvas that changes as we look. Light, the oldest companion of humanity, becomes a messenger whispering that certainty is an illusion and that knowledge itself shapes the world it describes. The truth remains elusive. Some call it a mystery of consciousness, others a puzzle of mathematics, others still an artifact of how we frame our questions. But whatever the ultimate resolution, one fact endures. Observation changes the game. It does not simply reveal what is already there. It alters what can be. It forces the photon to declare, collapses the wave of probabilities, or opens the door to countless worlds branching unseen. When you sit in a quiet room and turn on a lamp, you are not just illuminating space. You are participating in one of the most profound riddles science has ever faced. The light spilling across the floor is not just a stream of photons. It is a dance of potential and actuality, a silent negotiation between what is possible and what is observed. And though we may never fully explain why the universe plays by these rules, we cannot deny that it does. The observation of light is not a passive act. It is a transformation. It reminds us that knowledge is not free, that looking carries consequences, that the universe responds to inquiry in ways that defy common sense. To see is to alter. To measure is to create. And in that unsettling truth lies both the terror and the beauty of modern physics. Light pours into the world as if it were the most ordinary thing, yet behind its daily familiarity hides a paradox that still leaves science humbled. Photons, the quanta of light, are said to have no mass. They weigh nothing, not even a fraction of an atom. They cannot be weighed on any balance, nor do they rest quietly on any scale. And yet, these weightless messengers of the cosmos carry momentum. They strike surfaces, exert pressure, and push against matter with an invisible hand strong enough to move dust across space and sails across the void. How can something that has no mass possess the power to shove planets' atmospheres, ignite tails of comets, and one day perhaps carry ships between the stars? This is one of light's most enduring riddles, the truth that feels like contradiction. Step into the world of the everyday, and momentum seems inseparable from mass. A rolling stone gathers momentum because of its weight and velocity. A hammer swings with force because metal has heft. Even a tennis ball lobbed across a court depends on its mass to strike with speed. Mass multiplied by velocity. This is the language of Newtonian mechanics. To push, you must have weight. To carry force, you must bear substance. Yet photons, those massless packets of energy, break this rule. They travel at the ultimate cosmic speed limit, the speed of light, and though they have no rest mass, they deliver a push wherever they land. The explanation begins with Einstein's great insight. Energy and mass are bound in an equivalence, two faces of one coin. A photon may lack rest mass, but it carries energy, and energy in motion possesses momentum. A stream of light is a stream of energy moving forward, and that energy must obey conservation laws. Thus, when photons collide with matter, they impart momentum in proportion to their energy and frequency. What is remarkable is that the push, though small, is measurable. Shine a beam of light against a thin foil suspended in vacuum, and the foil tilts. Place an object in the path of the sun's radiance, and it feels a pressure from radiation itself, a whisper of a shove from the endless stream of photons pouring outward. This radiation pressure is no mere curiosity. It is an engine of cosmic design. Comets sprouting long, ghostly tails as they approach the sun do so because photons push against the dust and gas, sweeping them away in gleaming arcs. The dust in interstellar space feels the sun's breath not as wind of matter, but as a wind of light, pushing grains outward across billions of miles. Tiny particles too small for gravity to hold are blown into the darkness by the sheer radiance of starlight. The heavens are sculpted by these weightless carriers, every beam an invisible broom sweeping cosmic dust. Now imagine harnessing this power deliberately. The dream of solar sailing is born from the paradox of photons without mass. A solar sail is a craft propelled not by fuel, not by engines burning oxygen and hydrogen, but by the sunlight itself. Envision a vast sheet of reflective material, thinner than paper, but stretched across hundreds of meters, floating in orbit. Each photon from the sun strikes the sail and rebounds. Individually, the push is infinitesimal, a mere nudge. But the sun sends billions upon billions of photons every instant, and over time, their collective push accelerates the sail. Without fuel, without exhaust, such a craft could glide through the solar system, pushed forward by nothing but the endless tide of radiance. In fact, the physics works so precisely that space agencies have already tested it. Japan's Ikaros spacecraft, launched in 2010, unfurled a solar sail that spanned 20 meters. Sunlight alone drove it forward, proving that photons, though massless, could propel a machine through the void. The Planetary Society's Light Sail project has since demonstrated the same principle, showing that a new age of exploration may rest not on burning rockets, but on catching starlight like wind in a canvas. It is a poetry made real, ships sailing not upon seas, but upon the flood of photons streaming from stars. But even as engineering proves the concept, the paradox remains unsettling. If photons are weightless, how do they carry force? How can the most ethereal of particles, quanta that exist only as excitations of the electromagnetic field, push hard enough to alter orbits, ignite comet tails, and press upon spacecraft? The answer lies in a shift of perspective. In relativity, momentum is not defined purely by mass and velocity. It is defined by energy and motion. A photon's energy is tied to its frequency. The higher the frequency, the more energetic the photon. A gamma-ray photon, buzzing at the highest frequencies of the spectrum, carries a staggering punch compared to the gentle nudge of a radio wave photon. Energy in motion is momentum, and photons, though massless, are pure energy in flight. This invisible shove is measurable even on Earth. In laboratories, scientists have built instruments delicate enough to detect the pressure of light beams. Laser cooling, for instance, uses this principle to trap and slow atoms. By directing beams of photons against an atom, its motion is slowed, because each photon imparts a minuscule push. Arrange the beams carefully, and atoms can be cooled to near absolute zero, their jittering motions calmed by countless invisible taps from weightless quanta. This technique has opened new realms of quantum research, allowing scientists to study matter at temperatures where bizarre phenomena emerge. Light, weightless yet forceful, becomes a tool of control. Even our planet's climate whispers of radiation pressure. Earth's upper atmosphere, especially in the tenuous reaches where satellites orbit, feels the faint push of sunlight. For spacecraft with large surfaces, such as satellites with solar panels, this pressure matters. Engineers must account for it when plotting trajectories. For over weeks and months, the tiny push of photons shifts orbits, nudging machines along paths that gravity alone would not dictate. What seems fragile in a moment becomes decisive across time. The paradox of photons without mass also illuminates deeper mysteries of the cosmos. If photons can carry momentum, they can transfer it. When sunlight strikes Earth, it not only warms, but also presses faintly upon our world. When stars pour their light into the cosmos, they radiate momentum outward, balancing their internal furnaces against the gravity trying to collapse them. In the lives of massive stars, radiation pressure can determine fate. If the furnace burns too hot, the outward push of photons can exceed gravity's pull, driving fierce, stellar winds that strip away mass. The shaping of galaxies, the seeding of nebulae, the very cycles of star birth and death are influenced by the paradoxical shove of massless quanta. Here on Earth, it bends toward human imagination. Imagine a future where spacecraft unfurl sails kilometers wide, shimmering like silver leaves, catching the flood of light from our sun. At first, they move slowly, creeping like driftwood in a current. But time is the ally of light. Day by day, the invisible push compounds until the sails race between planets, outpacing rockets that once burned their fuel in minutes. Beyond the solar system, lasers could be aimed at sails, driving them faster still, perhaps even to fractions of light speed. This is the dream of Breakthrough Starshot, a project that imagines sending tiny craft to nearby stars within a human lifetime, carried on the breath of photons. A paradox becomes propulsion. A contradiction becomes destiny. Still, at the heart of all this lies unease. Science can describe how photons push, but not why weightless quanta should carry such tangible force. The equations balance neatly, the experiments confirm the predictions, but the intuition bogs. To carry momentum, should you not first carry mass? To push, should you not first weigh something? Yet the universe writes its own rules, and photons obey none but those. Perhaps the discomfort comes from our senses, evolved in a world where rocks fall because of weight, not because of energy. Light belongs to a deeper stratum of reality, one where mass is not the only path to motion. This realization ties back to Einstein's broader revolution. Energy and mass are equivalent, interchangeable under the right conditions. A photon may be massless, but its energy grants it momentum. When it strikes matter, it shares that momentum, producing pressure. The paradox dissolves not by denying the contradiction, but by reframing the question. Photons are not little stones flying through space. They are ripples of energy, and energy itself is substance enough to shove. Every dawn carries this paradox into our lives. Sunlight spills across landscapes, painting mountains and oceans with gold. But in those beams lies not just warmth, not just illumination, but force. Every photon landing on Earth presses with a touch too small to feel but immense when multiplied across the entire sphere of our planet. We walk in an invisible current, bathed in a pressure we never notice, yet one that shapes comets, stars, and perhaps our future voyages. And so, the paradox of photons without mass lingers as one of light's most poetic riddles. They weigh nothing, yet they push. They are immaterial, yet they sculpt the cosmos. They cannot be placed on a scale, yet they carry the power to move worlds. Each morning beam, each starlit ray is a whisper of that contradiction, a reminder that our universe does not always bend to the logic of human expectation. To watch sunlight glint across glass or shimmer in water is to see momentum without mass at work, a cosmic paradox hiding in plain sight. Light, so familiar that it spills through our windows every morning, hides a quality that stretches the imagination until it nearly breaks. Beyond its colors, its warmth, its paradox of particle and wave, there lies a stranger truth. Two photons can be linked in such a way that distance no longer matters. This linking, called entanglement, is one of the most baffling and revolutionary attributes in all of science. It suggests that light is not merely about illumination, not simply about carrying energy through space, but about carrying information in ways that seem to defy ordinary cause and distance. In entanglement, photons become twins that share a connection so deep that measuring one instantly influences the state of the other, no matter how far apart they travel. To imagine it, picture a candle flame flickering in the dark. From it, countless photons scatter outward in every direction, each one a packet of energy traveling at the cosmic speed limit. Now imagine creating two of those photons in a special way so that they are born together in the same quantum event. These twins are entangled. From that moment, their fates are woven together in a fabric that ignores the rules of space and time as we understand them. Separate them by inches, by miles, or by the width of the galaxy, and still, when one photon is measured, the other knows. The universe answers with coordination that cannot be explained by signals traveling between them, because no signal could move faster than light itself. This is the heart of the puzzle that drove Einstein to call entanglement spooky action at a distance. He recoiled at it, suspecting there must be hidden variables, some unseen bookkeeping inside the photons that predetermined the outcomes. Surely, he thought, reality cannot allow one particle to influence another instantly across space. Yet experiments have shown again and again that entangled photons behave precisely as quantum theory predicts, even when separated by distances that rule out any communication at light speed. The entanglement is real, and the universe plays by stranger rules than Einstein hoped. The origin of entangled photons lies in the quantum processes that create them. One common method is known as spontaneous parametric downconversion, a technique in which a single high-energy photon passes through a crystal and splits into two lower-energy photons. The pair must conserve the properties of the original photon, its momentum, its polarization, its energy, and so they emerge linked. Measure one, and you immediately learn something about the other. But the link goes deeper than shared history. Even when you don't know in advance how the photons will appear, their behaviors remain correlated in ways that no classical explanation can account for. What does this mean for light itself? It means photons are not merely messengers carrying energy from source to destination. They are also carriers of correlations that can stretch across any distance. When entangled, they form a single system, even when physically apart. This breaks the ordinary picture of space as a barrier. In quantum reality, separation does not sever connection. A photon in New York and its twin in Tokyo remain part of one indivisible whole. Consider the double slit experiment once again, that test which forced physicists to accept light's dual nature as both wave and particle. Now add entanglement. Fire entangled pairs through the slits, measure one, and you influence the interference pattern of the other. The results are consistent with the mathematics of quantum mechanics, yet they defy ordinary cause and effect. What happens in one place seems to ripple into another instantly. Light, when entangled, stops behaving like a local phenomenon and begins to reveal itself as part of a deeper, non-local reality. For centuries, science has relied on locality, the principle that influences must travel through space over time. Entanglement challenges that foundation. If photons can be linked across space, it suggests the fabric of reality itself may not be built from separate pieces, but from an underlying whole. Space might be less like a grid of independent points and more like a woven sheet, where tugging one thread shifts the entire weave. Light, in this view, is not just radiation but a probe of reality's deepest structure. The implications of this are staggering. Entangled photons are now used in experiments that test the very limits of physics. Bell's theorem, proposed by physicist John Bell in the 1960s, showed how entanglement could be tested against the idea of hidden variables. Countless experiments since then have confirmed quantum predictions. In 2015, loophole-free tests demonstrated beyond doubt that entanglement is not an illusion of incomplete measurements. Light truly exhibits correlations that transcend distance. The result is not a trick of instruments, but a truth about the universe itself. Entanglement is not only a philosophical riddle, it is also becoming a tool. Scientists now create and manipulate entangled photons to develop quantum technologies. Quantum cryptography, for instance, uses entangled pairs to guarantee secure communication. If two people share entangled photons, any attempt by a third party to measure or intercept them disturbs the entanglement, revealing the intrusion. It is a level of security not possible with classical signals. Quantum networks are being built where entangled photons link nodes across cities, creating the foundation for an internet that cannot be eavesdropped upon without detection. Quantum teleportation, another application, relies on entanglement as well. Though it does not teleport matter itself, it can teleport the state of a particle. Information about one photon can be transmitted to another distant photon instantly, with entanglement carrying the link. Experiments have successfully teleported photon states across kilometers of fiber optic cable and even between Earth and orbiting satellites. Light, when entangled, becomes not just a medium for seeing, but for transferring the very essence of information itself. Yet as powerful as these applications are, the fundamental mystery remains. What exactly happens in entanglement? Are photons somehow whispering to each other through a hidden channel we cannot perceive? Or is space itself an illusion, with entangled photons revealing the underlying unity of reality? Some interpretations suggest that entanglement shows us that the universe is not fundamentally local at all, that separation is a kind of illusion created by our limited perspective. Others propose that reality is built on information itself, and entanglement is the signature of that informational substrate. What makes this even more unsettling is that entanglement is not confined to photons. Electrons, atoms, even larger systems can become entangled. But photons provide the clearest window because they travel without mass, interact cleanly, and can be manipulated with exquisite precision. They are the laboratory's purest test case for entanglement. Through them, we glimpse the deep strangeness of quantum mechanics with unmatched clarity. Imagine holding a prism to sunlight, splitting white into its rainbow of colors. Each hue is a photon, speeding away at light speed. Now imagine that some of those photons are entangled pairs. Hidden in the rainbow is a connection invisible to your eye, a thread tying distant parts of the spectrum together. We see the beauty of light as color, but beneath that beauty lies a hidden order in which distance does not matter. Light becomes not just a spectacle but a bridge. It is tempting to imagine entanglement as magic, a kind of instantaneous messaging system across space. But it is not that simple. Entanglement does not allow faster-than-light communication, because the outcomes of photon measurements are random. What entanglement guarantees is that the randomness is shared. If one photon collapses into one state, the other collapses into the corresponding state instantly. The correlations are perfect, but no usable signal can be sent. This preserves the cosmic speed limit, even while entanglement teases the edges of what distance means. This subtlety matters because it keeps entanglement within the bounds of physics, even as it stretches our understanding. It does not break relativity, but it suggests relativity is not the full picture. Light, through entanglement, hints at a layer of reality deeper than space-time, one in which connection precedes separation. To live in a universe where light behaves this way is to live in a universe stranger than myth, stranger than dream. And still, entanglement is fragile. Entangled photons are easily disturbed by interaction with their environment. A stray atom, a piece of dust, a vibration in a fiber optic cable, all can destroy the delicate quantum link. Preserving entanglement over long distances is one of the great challenges of quantum communication. It is why satellites are being launched to test entangled links in space, where the vacuum offers fewer disturbances. The dream is to one day build a quantum internet spanning the globe, its backbone made of light that carries not only energy, but also unbreakable secrets. In all this, the poetic heart of light remains. These photons, born weightless, streaming endlessly, carry paradoxes that bend reason. They can strike a solar sail and push it through space. They can light the eyes of a child reading by a candle, and when entangled, they can show us that distance is not always a wall. They remind us that reality is more intricate, more subtle than our everyday senses allow. To gaze at starlight is to gaze not only across distance, but across entangled possibility. Somewhere, some photons that began together in the fires of stars are still connected, their fates bound, their information woven into the same thread. They may never be measured, never be noticed, yet they remain tied. Entanglement whispers that the universe is not a set of separate islands, but a sea in which everything may be linked. Light, in this sense, is not just illumination, but revelation, pointing toward truths that defy ordinary thought. As experiments grow more precise and technologies grow bolder, entanglement will remain at the center of discovery. Each new photon pair created in laboratories is a reminder that science is still climbing the wall of mystery, still reaching for an understanding of how the universe is stitched together. And in every entangled beam, every quantum link, light shows us that its greatest attribute may not be brightness, or warmth, or speed, but it's to reveal the hidden unity of the cosmos. Light has always seemed to us like the messenger of the present. It arrives in our eyes, illuminating the world around us, drawing a line between what is and what is not. We treat it as the boundary of reality, the courier that delivers immediacy. Yet when the equations of physics are written carefully, stripped of metaphor and laid bare in mathematics, something unsettling emerges. Light does not always seem to care about time the way we do. In some of the deepest formulations of physics, the equations describing light work equally well forward or backward. Past and future appear as mirrors. The beam that streaks outward from a star could just as easily be described as converging upon it from some future sky. Photons, it seems, do not march to the human arrow of time. This realization begins with the symmetry of Maxwell's equations. These four laws, the ones that unite electricity and magnetism, are time-symmetric. Write them in one direction, describing waves propagating forward in time, and the math holds. Reverse them, describing waves that collapse backward into sources, and the math still holds. Nothing in the equations forbids light from running time in reverse. For us, time is a river flowing one way, carrying memory forward and leaving the past behind. For light, the equations whisper of a mirror-like world where direction is irrelevant. Physicists call these solutions advanced and retarded potentials. Retarded potentials describe what we expect. A charge moves, and light radiates outward, carrying information into the future. Advanced potentials, by contrast, describe waves that converge from the future into the present, as if the photon's destiny is to arrive at a point, rather than to depart from one. Both solutions are valid. Both obey the laws. Yet in practice, we only ever seem to observe the retarded kind. Lightning strikes, and we see the flash after. A bulb glows, and light pours outward. But why should nature prefer one and not the other? when the math itself refuses to choose. Some interpretations suggest that perhaps photons exist outside our sense of time altogether. Because they travel at the speed of light, their own proper time, the time experienced from their perspective is zero. A photon emitted from a distant galaxy billions of light years away and one absorbed in your eye tonight experience no separation at all. For the photon, emission and absorption are a single event, collapsed into the same moment. From this viewpoint, the photon's existence is not stretched across time like ours, but pinned between two mirrors, its origin and its destination. We see it as a journey across billions of years. The photon knows only immediacy. This perspective explains why the equations allow time to run either way. If photons do not experience time, then whether they are described as leaving the past or arriving from the future makes no difference. The symmetry is built into their nature. It is our slower, heavier world that insists on a forward arrow, dictated by entropy and memory. Light, freed from the weight of mass, plays by rules we find alien. The weirdness grows when quantum mechanics joins the picture. In quantum electrodynamics, Richard Feynman introduced diagrams to represent the interactions of photons and particles. In those diagrams, photons can move not only forward in time but backward as well. An electron moving backward in time can be reinterpreted as a positron moving forward. Particles and antiparticles emerge from this symmetry, hinting that time itself may be less absolute than we think. The math does not forbid photons from behaving as though they are signals from the future, converging into the present. Experiments seem to hint at this strangeness too. Delayed choice versions of the double slit experiment, proposed by John Wheeler, show that decisions made in the present can appear to influence how photons behaved in the past. Fire photons through a pair of slits, but wait until after they pass to decide whether to measure their path or not. Incredibly, the interference pattern, or its absence, depends on that later choice. It is as if the photon knew in advance what experiment it would face, and its past was rewritten accordingly. The universe seems to allow a kind of retroactive logic, where the present reshapes the past. The quantum eraser experiments deepen the puzzle, measure which path the photon takes, and the interference vanishes. Erase that information later, and the interference reappears, as though the photon's past behavior was altered by what you chose to do after the fact. These results do not mean that humans can send messages to the past, but they do suggest that light's relationship with time is not bound by our ordinary sense of cause and effect. Past and future are entangled, woven together in a way that feels like mirror symmetry. Philosophers and physicists alike wrestle with what this means. Some argue that light reveals the universe as fundamentally timeless, that what we call time is simply a human perception of entropy increasing. Others suggest that the future is as fixed as the past, and photons expose that reality. They are not choosing a path but connecting two ends of a rope already tied. In this block universe view, past, present, and future all exist at once, and photons are threads weaving them together. Still, there is something haunting about the image of photons as mirror travelers of time. Every star you see at night, every candle flame, every lamp on a desk is not only sending photons outward into the future, but could equally be described as being pulled by their eventual absorbers. Your eye tonight completes the story of a photon born long ago. In some sense, you are always part of that photon's destiny. The equations allow this symmetry, and nothing in the mathematics says it is wrong. The consequences reach even into cosmology. The cosmic microwave background, the faint afterglow of the Big Bang, is a flood of ancient photons that have traveled across nearly the entire history of the universe to reach us. In one sense, they are the oldest messengers imaginable. In another, they have only ever existed as a link between the primordial fireball and your telescope. Time collapses for them. Their story is not billions of years of waiting, but a single instant stretched across space. Past and future mirror each other, and we are caught in the reflection. The unsettling truth is that light, in the deepest descriptions, does not recognize our arrow of time. It flows both ways in the equations. It cares nothing for the distinction between before and after. What we see as a beam radiating outward is equally valid as a beam converging inward. What we see as history unfolding might be, in part, the universe stitching together events across temporal boundaries. Photons are the embroidery threads, their patterns revealing that the fabric of time may not have edges at all. For daily life, of course, the arrow still holds. Cups fall from tables and shatter. They do not leap together and rise. The sun sets and does not reverse. Entropy marches forward, ensuring that memory runs one way. But light's indifference to that flow whispers that time's arrow is not absolute. It is a consequence of matter, energy, and entropy. Strip those away, and the timeless nature of photons comes into focus. They do not age, do not change, do not wait. They only connect, across what we perceive as the river of time. And so, in every sunrise and every starlit night, the paradox waits. Time runs forward for us, but for light. The past and future are mirrors. Our eyes catch photons born in fires long gone. Yet from their perspective, the journey was instantaneous. The glow in your room tonight and the light from a quasar billions of years away are the same kind of event. Timeless exchanges between source and observer. The mirror symmetry of time remains one of light's strangest attributes, a reminder that reality is not bound by human intuition. Imagine standing at the edge of an abyss so deep that not even light can escape. The very thing we rely on to see, to measure, to know, the swiftest traveler in the universe, meets its limit there. Light bends, light slows in its escape, and sometimes light never returns. Black holes are the most extreme stage for this drama, where the relationship between gravity and light reaches its most mysterious conclusion. And in that stage, we begin to glimpse truths about the universe that test the edges of comprehension. Albert Einstein predicted such a place long before the name black hole was even coined. His equations of general relativity told us that mass bends space and time, that the more massive an object is, the more it curves the stage of reality itself. Light, having no mass, should glide freely. Yet light always follows the curves of space-time. Put enough mass into a small enough region, and space-time curves so violently that light itself is caught, forced into an endless orbit, or dragged into disappearance. Here, the speed of light, so constant and unbeatable everywhere else, is no longer a guarantee of escape. From far away, we see the effect in slow motion. Light struggling up from the surface of a massive star loses energy. Its frequency shifts redder, stretched thin by gravity. Astronomers call this gravitational redshift, the first whisper of light slowing under the grip of mass. But near a black hole, the effect is magnified beyond reason. Light fleeing the edge is stretched until it fades invisible, as though gravity is draining away its color and strength. And once a photon crosses the boundary we call the event horizon, it is gone from our universe. It is not merely dimmed or hidden. It is unreachable, a thread cut from the fabric of observable reality. What does this mean for us, living creatures whose eyes depend on light? It means that a black hole carves a shadow into the cosmos, not a shadow in the ordinary sense, like a tree blocking sunlight, but a region where no light can emerge to tell us what is there. The event horizon is not a physical wall. It is geometry itself saying no farther. And yet the story does not stop at disappearance, because just outside the horizon, light still performs its dangerous dance, curving into strange orbits called the photon sphere. At this radius, light does not fall in immediately, nor does it escape. Instead, It circles the black hole endlessly, a ring of trapped photons that form a luminous halo around darkness. In reality, the orbit is unstable. Any slight disturbance sends the photon inward to vanish or outward to escape. But this photon sphere creates the eerie edge that astronomers dream of capturing, a perfect circle of light outlining an otherwise invisible hole. It is here that the paradox of light and gravity becomes almost visible to us. The Event Horizon Telescope project achieved this feat in 2019, stitching together radio signals from telescopes across the globe to produce the first direct image of a black hole's shadow. The object was M87 star, a supermassive black hole in the heart of the Virgo cluster, 55 million light-years away. What the world saw was not the black hole itself, that remains forever hidden, but the halo of light bent around it, a glowing ring marking the absence at the center. That faint orange circle carried within it a human triumph. We had at last seen the place where light is undone. Why does relativity predict such bending? The answer lies in how space-time itself is warped by mass. Light, which must always move at the same speed in a vacuum, follows the straightest possible path through space-time. But in curved space-time, straight is no longer the same as flat. The photon's journey is bent along the fabric, much like a marble rolling along a warped sheet. Near the Sun, this bending was confirmed during an eclipse in 1919, when starlight was observed to shift as it passed close to the solar disk. But near a black hole, the warping becomes so severe that paths loop back upon themselves, and the ordinary rules of distance collapse into new definitions. Inside the event horizon, paths twist in a way that astonishes the imagination. Every direction points inward. To fall in is not a matter of gravity tugging you downward. It is geometry itself redefined so that all futures lead to the singularity. For light, the supreme traveler, there is no detour, no shortcut, no escape. Once inside, the photon is part of the singular fate. The thought is unsettling not only because of what it means for matter and radiation, but because it suggests a boundary to knowability. Physics, which thrives on observation, finds here a veil it cannot lift. And yet, paradoxically, black holes radiate. Stephen Hawking showed that quantum mechanics and curved space-time together produce a faint glow, Hawking radiation, leaking from the horizon. Virtual particles near the edge are separated by gravity, with one escaping as real energy and the other swallowed by the whole. If this prediction is true, then light does leave, but in whispers, not shouts. Hawking radiation has never been observed directly, but its implication is profound. Even the darkest hole is not entirely silent. In the meantime, astronomers look for indirect signatures of light's peril. When matter spirals into a black hole, it heats to extreme temperatures, emitting X-rays and gamma rays before it crosses the horizon. This accretion disk glows fiercely, one of the brightest phenomena in the universe, and yet its light is shaped by relativity. Time slows near the horizon, and to a distant observer, infalling matter appears frozen, fading, never quite vanishing. Light betrays the strangeness of time itself here, showing us that clocks run differently in the presence of extreme gravity. Think then of the role light plays in our understanding of black holes. We cannot see inside, but we can trace the curves outside. We cannot observe the singularity, but we can watch how photons bend, vanish, or whirl in their impossible orbits. It is as though light sketches the outline of a forbidden realm, chalk on the edge of a cosmic door. In its bending, in its slowing, in its disappearance, it teaches us more about gravity and space-time than any equation alone could. And yet, even with all our measurements, there is mystery. Does information truly vanish when light is lost into a black hole? Or does it find some way to be preserved, encoded in the surface of the horizon, waiting to be released in ways we do not yet grasp? This information paradox remains one of the great unsolved questions of physics. Light, which always carried knowledge to us before, now carries uncertainty. Its silence inside the black hole speaks louder than any message. It is worth pausing here in this image of light silenced to realize what it tells us about existence itself. The cosmos is not boundless openness. There are edges, not in the sense of walls, but in the sense of places where our tools, vision, photons, science, reach their limit. Black holes remind us that the universe has horizons beyond which not even the swiftest messenger can cross. And yet those same horizons offer us a gift, a glimpse of the most extreme reality imaginable, written in curves of light. The shadow of a black hole is more than an astronomical curiosity. It is a symbol of the tension at the heart of physics. Light, the carrier of knowledge, the thing that illuminates truth, can be trapped, bent, and undone. Gravity, the oldest force, weaves cages even photons cannot break. Where the two meet, our theories strain, and the deepest questions about space, time, and information wait. In that darkness, we see not only absence but the outline of new understanding yet to come. The story of light inside the black hole's shadow is not one of failure, but of humility. It tells us that even with our most powerful telescopes, even with equations that span galaxies, there are places where mystery remains sovereign. And yet, light still guides us to those thresholds, curving around the edges, whispering of the shape within. Relativity's grip on the beam is not a prison we despair at, but a boundary we press against, knowing that in its silence lies the next chapter of discovery. When you look at a rainbow arcing across the sky after rain, you see only a sliver of what light truly is. The reds, oranges, yellows, greens, blues, and violets stretch like brushstrokes across the air. But the truth is both humbling and astonishing. This rainbow is incomplete. The visible spectrum, the colors your eyes are tuned to, is only a narrow slice of a much wider reality. On either side of it lie vast oceans of invisible light, ultraviolet and infrared, real, powerful, and woven into your life even though you cannot see them. They are reminders that human perception is not the full story of the universe, but merely a filtered window, one that leaves most of reality hidden behind closed shutters. The human eye is a remarkable machine, evolved over millions of years to detect survival cues. Our retinas contain cells sensitive to particular wavelengths, ranging from roughly 400 to 700 nanometers. That small band is enough to let us see the richness of nature, the green of leaves, the shimmer of water, the fire of sunsets. But it is not enough to reveal the entirety of what surrounds us. Below 400 nanometers, light shifts into ultraviolet, invisible yet potent. Above 700 nanometers, light becomes infrared, still beyond our vision but pressing constantly upon our skin. To live as a human is to swim in a sea of light, but to perceive only the shallow waters. The deep currents, ultraviolet and infrared, flow on unnoticed, except through their effects. Ultraviolet light, often shortened to UV, is a paradox of nature. On one hand, it is destructive. Too much exposure damages skin cells, disrupts DNA, and causes the painful burn we call sunburn. Yet on the other hand, it is essential. Ultraviolet radiation, striking the skin, triggers the production of vitamin D, a compound vital for bone health and immunity. Without UV light, our bodies would falter. With too much, they suffer. This double-edged nature makes ultraviolet a light of danger and necessity, a reminder that energy can both create and destroy. It is light our eyes cannot see, but our bodies cannot ignore. Infrared light tells a different story. Though invisible, we feel it every day as heat. Sit near a campfire, and you sense the warmth against your skin. Step out into the sunlight, and even without seeing it, infrared waves bathe you, transferring energy as a soft embrace. Infrared radiation is longer in wavelength than visible red light, invisible yet deeply familiar. Modern technology has given us the means to see it with instruments. Thermal cameras paint glowing landscapes from temperature differences, showing us animals in the dark, electrical systems overheating, or the body heat of friends standing across a room. What was once invisible becomes color-coded through sensors, revealing that the world is never truly dark. It only hides light we cannot perceive. Animals remind us of our limitations more vividly. Bees and butterflies see ultraviolet markings on flowers, patterns that guide them to nectar like landing strips painted in wavelengths we cannot imagine. Birds see a richer world too, their plumage shimmering in ultraviolet, turning what looks drab to human eyes into radiant displays in avian vision. Pit vipers and some beetles sense infrared, detecting the faint heat signatures of prey or predators. What we call reality is not the same reality to them. To a bee, a meadow is striped and patterned with ultraviolet lines. To a snake, the forest is overlaid with glowing heat maps. To us, these dimensions are invisible, absent, unknowable without tools. Science has given us those tools, and with them we have begun to uncover the richness beyond sight. Ultraviolet telescopes peer into the heavens, showing galaxies blazing in high-energy light, young stars pouring out radiation as they ignite nuclear fire. Infrared telescopes, like the James Webb Space Telescope, open the universe's cool, dusty corners, revealing planetary nurseries, the faint glow of galaxies born soon after the Big Bang, and even the heat of exoplanets circling distant suns. In each case, what our eyes cannot see becomes a story of cosmic evolution. Entire chapters of the universe's history lie written in invisible ink, legible only with instruments tuned beyond the visible spectrum. The practical uses of these invisible bands extend into everyday life. Ultraviolet sterilizes water and surfaces, killing bacteria and viruses. It reveals counterfeit banknotes through fluorescent dyes invisible in ordinary light. Infrared guides airplanes during fog, powers television remote controls, and allows astronomers to see through dust that would otherwise obscure the cosmos. Soldiers wear night vision goggles that amplify faint infrared, turning night into a surreal green glow. Firefighters carry thermal imagers into smoke-filled rooms, guided by the heat outlines of trapped survivors. Invisible light in these moments becomes the difference between ignorance and awareness, between survival and tragedy. Yet there is something philosophically unsettling about ultraviolet and infrared. They reveal that our perception of reality is partial, that what we call the world is constructed through the narrow filters of our biology. We walk outside and think we see everything illuminated, yet we are blind to most of the radiation pouring down. We sit in a room and believe we see it fully, yet infrared light paints a hidden landscape of warmth and motion. What would the world look like if we could perceive these bands naturally? Imagine colors beyond colors, a new spectrum opening like a second rainbow across the sky. The sunlight would shimmer with unseen shades. Flowers would blaze with ultraviolet signs. The night would be filled with glowing auras of heat. Our definition of normal vision would dissolve. That thought carries us into a deeper truth. Light, in all its forms, is impartial. It simply is. Visible, invisible, harmful, helpful. It exists whether we detect it or not. Our eyes are tuned to a useful slice of it, but usefulness is not completeness. The universe overflows with radiance across the spectrum, from the highest energy gamma rays to the longest radio waves. Ultraviolet and infrared are just two thresholds where the limits of our senses become obvious. They remind us that perception is not reality but interpretation. We live inside the comfort of human filters, While the true light of the cosmos extends far beyond our reach, there is poetry in this limitation. Just as we cannot stare directly into the sun without being blinded, we cannot stare directly into the whole spectrum of light without losing ourselves. Our bodies restrict us to what we can handle, but with instruments, with thought, with imagination, we stretch those boundaries. The ultraviolet markings on a butterfly's wings become visible through photography. The infrared heat of a galaxy hidden behind dust becomes a detailed image through a telescope. Slowly, patiently, we are learning to borrow senses from machines, to see not with our eyes alone, but with the eyes of science. And yet, the wonder remains. Stand outside at night, feeling the cool air around you. Above, stars shine in visible light, but they are also streaming invisible radiation. Ultraviolet bursts from hot blue giants, infrared whispers from dying red stars. Your eyes see pinpricks of white. In truth, each star is a symphony of light beyond your senses, playing on frequencies your body cannot hear. The universe is richer, louder, brighter than you will ever naturally perceive. And perhaps that is the greatest reminder. The fact that light still eludes complete explanation is not a failure, but a gift. It gives us mystery, depth, an invitation to keep seeking. So when we speak of ultraviolet and infrared, we are not speaking of abstractions, but of dimensions hidden in plain sight. They touch our skin, guide animals, shape ecosystems, and fuel technology. They pierce clouds of cosmic dust and sterilize hospital rooms. They harm and they heal, they reveal and they conceal. They are the colors beyond human eyes, the proof that our perception is never the final word. We live, always, inside a larger radiance, one that demands humility. Perhaps that is what makes the study of light so endlessly compelling. Every discovery, every new wavelength captured, every invisible pattern revealed, reminds us that the world is not limited by what we can see. It is shaped by what exists, whether or not our senses confirm it. Light, in all its forms, is a language the universe speaks. We hear only part of the sentence, but with science, with patience, we learn to translate more. As you close your eyes and drift toward rest, let this thought linger. The colors you see are only the beginning. Around you, beyond sight, the air is alive with ultraviolet and infrared, with patterns and stories your body cannot perceive. Yet they are there, just as real as the stars you look up at, just as constant as the warmth you feel from the sun. And in their invisible glow lies the reminder that mystery still lives all around us, that even in light, the most familiar of things, there remain secrets we have not yet unraveled. The speed of light is more than just a number on a chart of physical constants. It is the cosmic boundary stone, the ultimate speed limit woven into the fabric of reality. Written as c in equations, measured at about 299,792 kilometers per second, it defines what can happen and what cannot. No signal, no particle with mass, no piece of information can outrun it. And yet, for all its centrality, we do not know why it has the value it does. We know that it is fixed, unchanging and absolute, but not why the universe chose this number and no other. This constant both anchors physics and haunts it with mystery. Our story begins with James Clerk Maxwell. When he unified electricity and magnetism in the 19th century, his equations contained constants related to the electric and magnetic properties of space itself. Combine them, and out emerged a speed, one that matched the measured speed of light. The revelation was staggering. Light was an electromagnetic wave, and its speed was not arbitrary but determined by the fabric of the vacuum itself. Long before relativity, Maxwell had shown that the universe carried within it a built-in velocity, a natural pace for waves of light. Then came Einstein, who asked what would happen if you tried to chase such a wave. Imagine moving at half its speed, or 9/10, or 99%. According to common sense, if you ran fast enough, you should catch up, see the wave frozen, its peaks and troughs standing still. But Einstein realized this could not be. Maxwell's equations did not allow for stationary light. No matter how fast you went, light would always race ahead at the same speed. From this realization, the special theory of relativity was born in 1905. Relativity rewrote the very structure of space and time to preserve the constancy of c. Clocks tick slower as you move faster. Lengths contract along the direction of travel. Mass grows as speed increases. All these distortions occur so that, for every observer, the speed of light remains unchanged. It is not that light adapts to us, but that space and time adapt to protect light's speed. In this sense, c is not just a speed. It is the cornerstone of reality's geometry. It defines how cause and effect are ordered, how simultaneity is relative, how energy and mass are linked. Indeed, Einstein's famous equation E equals mc squared would mean nothing without c. It shows that mass can be converted into energy and energy into mass, with the conversion governed by the square of the speed of light. Nuclear energy, the fusion of stars, the annihilation of matter and antimatter, all of these processes unfold because c is the link between matter and radiance. The constant appears again in general relativity, shaping how space-time curves around mass and energy. It is the measure against which gravity's warping is compared. Without c, there is no relativity, no modern physics, no coherent picture of the universe at all. And yet, for all its importance, we are left with an unsatisfying question. Why this value? Why 299,792 kilometers per second? Why not slower? Why not faster? In units where other constants are set to 1, c becomes the scale that determines the relationship between space and time. It is the conversion factor between distances and durations. 1 light second is not just a poetic image, but a unit of length defined by c. Our entire system of measurement, from GPS satellites to deep space communication, rests upon it. But still, no theory tells us why the universe settled on this number and no other. It is one of those constants we measure, not derive, a given of existence. Consider what would happen if c were different. If it were slower, the universe might look utterly alien. Relativity would enforce stronger distortions at lower speeds. Everyday life might reveal time dilation and length contraction in ways we now encounter only in particle accelerators. Stars might form and evolve differently, nuclear reactions unfolding under altered balances of energy. If c were faster, perhaps the coupling of mass and energy would change. Perhaps the universe would expand differently. Perhaps no stable atoms would exist at all. Physicists speculate, but the truth is that without c being what it is, we might not be here to wonder at all. The constancy of light speed also sets the horizon of the knowable. Because no information can outrun c, we can see only as far as light has traveled since the beginning of the universe. The cosmic microwave background marks the edge of our visible cosmos, the point beyond which light has not yet had time to reach us. This horizon is not a wall, but a limit defined by c and the age of the universe. Every telescope, no matter how powerful, peers into a bounded past, its edge marked by this constant. In that sense, c is not just a speed, it is the size of our cosmic vision, and it defines the difference between possible and impossible. Faster than light travel, the dream of science fiction collides with relativity at every turn. To accelerate a mass to c requires infinite energy. To exceed it is to leave behind causality itself. Events could occur out of order. Effects could precede causes. Paradoxes would proliferate. The constant is not just a barrier, but the guardian of logical order in the universe. It is the line that preserves time's arrow from unraveling. Even so, human imagination pushes against this limit. Wormholes, warp drives, shortcuts through higher dimensions. These ideas try to find paths around C. They exploit the fact that relativity does not forbid space-time itself from stretching faster than light. Indeed, in the early moments after the Big Bang, inflation expanded space faster than C, carrying galaxies apart without violating the rules of local motion. But photons themselves, moving through that fabric, remain bound to their constant pace. No matter how wildly the stage shifts, the dancer of light steps only at one speed. At the quantum level, the mystery deepens. Photons always move at C. They cannot exist at rest. From their perspective, time does not pass. A photon born in the heart of a star and absorbed by your eye is part of a single timeless event. For you, billions of years may have elapsed. For the photon, there was no journey. This timelessness is part of why the constant feels so absolute. It is not just a property of motion, but of existence itself. To be a photon is to be bound to C. Physicists continue to ask whether the constant might have been different in the early universe, whether C might change over time, however slightly. So far, observations suggest it is indeed constant, unwavering across billions of years and billions of light years. But the question itself is revealing. We wonder because we do not know why the number is what it is. It is not explained, only observed, an anchor with no chain. And so, when we speak of the speed of light, we are speaking not only of a velocity, but of the architecture of reality. It defines how matter and energy relate, how time and space are joined, how cause and effect unfold. It sets the reach of our vision and the boundaries of our dreams. Yet it is, at its heart, a mystery. We do not know why it is the value it is. We only know that without it, the universe would not exist in the form we know. Every time you look at a clock adjusted by GPS, you are relying on C. Every time you look up at starlight, you are looking across years measured by it. Every time you imagine the cosmos, its vastness is drawn not only in kilometers but in light years, distances defined by this constant. The speed of light is not just a property of physics, it is the ruler by which reality measures itself, and perhaps that is what makes it beautiful, that the universe is not arbitrary chaos but structured by a constant, a number that appears everywhere, from relativity to quantum electrodynamics, from cosmology to technology. And yet, that structure leaves room for wonder, because we do not know why. The constant that rules the cosmos is both the most certain thing in physics and one of the deepest mysteries of all. Light has guided humanity for as long as we have drawn breath, and yet, after centuries of study, after telescopes peering across billions of light years and supercolliders smashing particles into fragments of fragments, the simplest question still refuses to yield. What is light, really? We can describe it in equations, measure it with extraordinary precision, bend it with lenses, trap it with mirrors, split it into colors, and harness it in lasers and satellites. But when the final layer of explanation is peeled back, what remains is a stubborn mystery, a core that has eluded clarity since the first torch lit the first cave wall. Light illuminates everything, and yet it will not allow itself to be fully illuminated. Physicists have tried to pin it down through many revolutions. To Newton, light was a stream of corpuscles, tiny particles flying straight and fast. To Huygens, it was a wave, rippling across some invisible medium. To Maxwell, it was the electromagnetic field, vibrations of electric and magnetic energy moving together. To Einstein, it was quanta, photons, packets of energy that explained the photoelectric effect. To quantum mechanics, it is both wave and particle, depending on how we look, or perhaps neither, existing instead as a probability cloud that collapses when measured. Each framework explains some part of light's behavior, predicts experiments correctly, and drives technology, and yet each framework falls short of capturing the whole. Take photons. In our current language, they are quanta of the electromagnetic field, indivisible packets of energy, each with no rest mass but with momentum. This concept explains radiation pressure, explains solar sails, explains why atoms absorb and emit light only at discrete frequencies. But what exactly is a photon? Is it a particle in the classical sense? A tiny billiard ball? Clearly not. It spreads like a wave, interferes with itself, and exists in superpositions. Is it a wave? Not exactly, because it arrives at detectors as single clicks, indivisible and precise. The photon seems to live in two contradictory categories, refusing to collapse into our language. It is not that it flickers back and forth between wave and particle. It is that our categories are insufficient. Quantum electrodynamics, or QED, is the most precise theory ever created to describe light. It treats photons as excitations of the electromagnetic field, interacting with charged particles through the exchange of virtual quanta. Its predictions are astonishingly accurate, agreeing with experiments to 1 part in a trillion. Every laser, every satellite communication, every MRI machine owes its existence to QED. Yet even within this triumph, mystery remains. Feynman himself admitted it. I think I can safely say that nobody understands quantum mechanics. The equations work, but what they mean is slippery. Are photons real objects or bookkeeping devices? Are virtual particles physical or mathematical? The success of QED hides the fact that our conceptual grasp is tenuous. We can calculate with exquisite power, but when asked to explain what light is, our answers unravel into paradox. Consider the double slit experiment once again, that haunting demonstration repeated with light, electrons, even molecules. Fire photons one by one, and they create interference patterns as though each interferes with itself. Place detectors at the slits, and the pattern vanishes. Observation changes the outcome. How can something that is supposed to be fundamental alter its nature simply because we looked? What is it we are observing? A photon traveling 2 paths at once? A wave function smeared in possibility? Or are we glimpsing something even deeper? That reality itself is relational, defined not in isolation but in interaction. Light seems to insist that our categories, object, path, cause, are provisional scaffolding, not ultimate truth. Then there is relativity's view. Light travels at the ultimate speed limit, c, the constant that reshapes space and time themselves. For a photon, proper time does not exist. Emission and absorption are a single timeless event. From our perspective, starlight takes millions of years to cross the void. From the photon's perspective, if such a thing exists, there is no journey, no duration, only the instant of creation and destruction. What does this mean for what light is? Can something without time truly be said to exist in the way matter does? If photons do not age, do not experience distance, then perhaps they are less particles and more connections, threads sewing together events across space-time. Modern experiments deepen the unease. Entanglement shows that photons can be linked across vast distances, their states correlated instantly. Delayed choice quantum erasers suggest that future measurements affect past behavior. Quantum teleportation uses photons as carriers of pure information, yet what is being carried is not substance, but state. Light begins to look less like an object and more like a messenger of possibility, a mediator between the abstract language of mathematics and the concrete world we observe. And yet, for all the philosophical vertigo, light remains intensely practical. Engineers build lasers that focus coherent photons into beams strong enough to cut steel. Fiber optic cables guide photons across continents, carrying voices, images, and data in pulses of invisible light. Astronomers capture photons that left distant galaxies billions of years ago, using them to map the structure of the cosmos. Medical devices use light to image the body without harm, or to perform surgeries with precision. Every time you glance at your phone, photons strike your eyes, carrying information. In daily life, light is the most dependable companion. It is everywhere, constant, reliable. And yet, beneath this familiarity, its essence remains elusive. Perhaps the mystery lies not in light itself, but in our insistence on fitting it into human categories. Wave, particle, field, these are metaphors born from our macroscopic experience, stretched to describe something fundamentally different. Light may not be wave or particle in any ordinary sense. It may be something else entirely, something for which our language has no word yet, and our intuition has no anchor. The photon is both a unit of energy and a ripple of probability, both timeless and fleeting, both local in its impact and non-local in its correlations. It is not that we do not understand light. It is that we may not yet have the right concepts to ask the question correctly. And so the mystery persists. Even with quantum electrodynamics, lasers, satellites, and supercolliders, we return to the same haunting silence. What is light really? Is it energy, information, connection, or all of these at once? Is it a substance of reality, or a shadow of deeper structures? Perhaps light is the universe's way of reminding us that complete knowledge is an illusion, that wonder must always remain. The paradox is almost poetic. Light is what reveals. It illuminates objects, makes the hidden visible, carries the colors of the world into our eyes. Without light, there is no vision, no seeing, no knowing, and yet light itself is the one thing that will not let itself be fully revealed. It remains the greatest enigma of all, glowing just beyond the reach of certainty. And perhaps that is fitting. If we had solved it completely, light would become mundane, its beauty reduced to formula. Instead, it stands as both tool and mystery, practical and profound. We wield it in technologies that shape civilization, but we also stare at it with awe, knowing that beneath every photon lies an unanswered question. That question keeps science alive, keeps curiosity sharp, keeps the universe from becoming small. So when you step outside tomorrow and feel the sun's warmth, or when you light a candle in the dark, or when you look up at the stars, remember this. Every photon that reaches you is a messenger of mystery. It carries not only energy but paradox, not only illumination but a whisper of the unknown. We do not yet know what light really is, and that truth, unfinished, unresolved, is itself a gift. Light is the most ordinary thing in the world, and at the same time, the most extraordinary. It greets you when you wake, spilling through a window in warm shafts across the floor. It follows you outdoors, bouncing from clouds, glinting off water, shimmering in leaves. At night it withdraws, leaving only the cold pinpricks of starlight to remind you that darkness is never complete. In every moment of life, light is there. It is the medium of sight, the reason for color, the carrier of warmth, the silent companion that makes existence visible. And yet, when we chase it into the depths of science, when we press our questions as far as they can go, we discover that this most familiar presence is also the most enigmatic. Light illuminates everything but itself. It reveals the world yet refuses to be revealed completely. Think back to the arc of discovery. From the first torches and oil lamps, humanity suspected that light was not just fire, not just smoke and flame, but something more subtle. Newton broke white light into colors with a prism, showing that brilliance was not simple but composed of hidden hues. Young's slits proved light could interfere like rippling water, and Einstein's photons showed it could strike like particles. Maxwell's equations united electricity and magnetism, and relativity placed light at the very heart of space-time structure. Quantum mechanics turned light into quanta, excitations of a field and entanglement revealed that photons could share connections across space. And still, every advance left us with more questions than answers. Light grew clearer and stranger at the same time. Lasers, fiber optics, and satellites have made light our most powerful tool. It carries your voice across oceans, beams data through space to a spacecraft orbiting Saturn, burns through metal in a factory, and performs delicate surgery in the human eye. Telescopes ride on photons to capture galaxies at the edge of time. Cameras freeze photons into images that define memory and culture. Our entire civilization rests on manipulating and controlling light, bending it into signals, pulses, beams, and patterns. Yet this mastery is not the same as understanding. We can build with light, but when asked what it is at its core, we hesitate. We say wave, we say particle, we say probability, but none of these words quite fit. And so light remains a paradox. It has no rest mass, yet it carries momentum. It moves at a constant speed, yet experiences no time. It can act like a wave, spreading into interference patterns, yet it can act like a particle, arriving as single clicks on a detector. It can exist in superpositions, in entanglements, in correlations that defy space itself. Each description works in some context, but none captures the whole. Light is at once field, particle, connection, energy, and mystery. The more we discover, the less we can reduce it to any one thing. This is perhaps what makes light not just a physical entity, but also a symbol. Philosophers, poets, and mystics have long turned to it as a metaphor for truth, knowledge, and divinity. To see the light has always meant more than vision. It has meant understanding, awakening, clarity. Light pierces the darkness of ignorance. Light is the first act of creation in myth, the spark that transforms chaos into cosmos. The fact that modern physics leaves light as an unresolved mystery only deepens this symbolic resonance. Light is not only illumination, it is an endless invitation to wonder. Every photon that strikes your eye tonight carries with it the paradox of the universe. Some were born in your lamp or screen a fraction of a second ago. Others began their journey in the heart of a star billions of years in the past, traveling across cosmic gulfs to arrive exactly where you stand. Yet for the photon itself, there was no travel, no waiting, no time at all. From emission to absorption, its existence was timeless. You see the starlight as ancient. The photon knows only immediacy. In that difference lies one of the greatest mysteries of existence, a reminder that the world as we perceive it is not the world as it truly is. And so, resting in the glow of light, you rest in the glow of paradox. You live in a universe where the most familiar thing, illumination itself, still resists final explanation. You are bathed in photons every waking moment, nourished by them, guided by them, protected and sometimes harmed by them. They are the threads that sew together perception and survival, the carriers of both beauty and information. Yet they are also whispers from a deeper reality, reminders that beneath the surface of understanding lies an inexhaustible well of mystery. This is not failure, it is grace. If light were fully explained, if it fit neatly into our concepts, it would no longer be a source of awe. But because it resists us, it keeps curiosity alive. It keeps science restless, keeps philosophy awake, keeps art inspired. Light is not only the medium by which we see, it is the reminder that there is always more to see, always more to learn. Every beam of sunlight, every candle flame, every star in the night sky is both explanation and question, both answer and riddle. So perhaps the greatest lesson light offers is humility. It tells us that the universe is larger than our categories, stranger than our theories, richer than our senses. It tells us that knowledge is not about final closure, but about continual discovery. It tells us that even the most ordinary things, the glow of a bulb, the warmth of the sun, are layered with mysteries deeper than imagination. Rest then in the glow of this paradox. Let light be both your comfort and your puzzle. Let it guide your eyes to the world and your mind to the questions beyond it. You do not need final answers tonight. It is enough to know that you are surrounded by something that is both utterly familiar and utterly beyond comprehension. Light will greet you again in the morning, spilling across your walls, carrying with it the warmth of certainty and the chill of mystery. And in that blend lies the wonder of existence itself.